Good, good morning, everybody. Can you hear me? Just if I need to. Thank you. And thank you for my back. All right, good morning, everybody. We have another great day ahead of us, so I'd like to get started and welcome you all to day 3 of this Planetary Defense Conference 2025 in beautiful Stellenbosch. The clouds are parting, we're seeing the mountains again. So I hope that's promising for today. I have a couple of quick announcements today. So if you haven't registered yet, after the session ends today around 4 p.m., we will first have a group picture outside. We'll announce it again, but we will go outside to the restaurant downstairs and keep left to there's some green spot with nice scenery in the background. And that will be before, if you have registered for the buses that go to the VA waterfront, they will be boarding around 16:30. I don't know if you can still sign up if you haven't done so yet. I think the due date was yesterday, but you can try. And so pictures before the buses, and then we head down to the waterfront and enjoy a nice evening with the IMAX movies and some dinner. And I just want to give a shout out to everybody online as well. Apparently we have people from Texas online currently. Good morning. Happy to see you all so dedicated and involved. And speaking of being involved, the app is not just for the virtual participants, it's also designed for your in-person experience to enhance it. Of course, a lot is happening here on stage. But there's still polls and surveys open. We do want to hear from you from day one. We're going to have a few more today and in the coming days. So if you find some time, you don't have to do it now, but in the coffee break or once you remember to check the app and see what good stuff is there to complement your experience, whether you're in person or online. And with that, I'm happy to move to the first session. That is the NEO Discovery, and Marco and Davide will share that, and I'll hand over to Marco.
It works. Does it work? Yeah, it does. So, yes, thank you very much for joining for the session number 4 of this PDC. It's going to be on NEO Discoveries, and we're going to start with a virtual talk. I hope that Richard Wainscott is online. He's going to talk about the Pan-STARRS search for near-Earth objects 10 plus years old and going strong. I see Richard on screen. I see the presentation there. I don't see the timer reset yet. If you can reset the timer, maybe down there. Perfect. Yep. And so all yours, Richard. Thank you.
Okay, you hear me? Do you hear me okay? Are you able to hear me?
Yes, we can hear you. Loud and clear.
All right. So, okay, thank you. So, good morning from Hawaii, where it's evening.
Can you put the presentation full screen?
Yeah. Sorry. I'm talking about the Pan-STARRS search for near-Earth objects. So Pan-STARRS is 2 1.8-meter telescopes located in Maui, near the summit of Haleakala. Each is a big telescope with a large field of view, 7 square degrees in total. Here's a look at the Pan-STARRS 2 telescope. This is the sort of the more modern, newer of the 2 telescopes. So we are able to survey the sky from the North Celestial Pole all the way to about -50 in the south. We obviously don't do quite so well in the south. We have now a big solar telescope in the way. We avoid the galactic plane mostly, and our search is funded by the NASA Near-Earth Object Observations Program. So NASA's been tasked with finding 90% of the objects with diameter bigger than 140 meters and As of now, about 45% of those have been found, so we're about halfway there. But when Pan-STARRS started in 2010, only about 18% of those had been found. And one of the major strengths of Pan-STARRS is actually finding these big objects, and it is the leading survey for the discovering these bigger objects, and we found 54% of the total in the last 3 years. So Pan-STARRS once started in 2010. For the first 4 years, it was doing an all-purpose survey, spending very little time looking for NEOs, but then funding for that survey ran out, and Pan-STARRS has since then been funded by NASA to search for near-Earth objects, and 90% of the observing time is devoted to this survey. Pan-STARRS 2 became fully productive in 2021 after a problem with the secondary mirror was corrected. The way we find near-Earth objects is we take a sequence of 4 images spaced over about an hour. We find moving objects that way, and the near-Earth objects are objects that usually have unusual motion because they're close to the Earth. So this is about the amount of sky that Pan-STARRS can see in one lunation. You can see in this pattern here that we've avoided the galactic plane, but we can cover most of the available sky with one telescope, so we can cover it twice with 2 telescopes if the weather cooperates, and the weather has not cooperated very well so far in 2025. This is a look at the discoveries by survey, and Pan-STARRS is the pink object, the pink color on that plot. These are the 140-meter and larger objects, and Pan-STARRS is pink again. These are all NEOs discovered by listed by survey. Here are some statistics. We've reported over 110 million observations to date, discovered 563,000 asteroids, 70,000 numbered asteroids. Just about every numbered asteroid we have seen, and to date, a little over 12,000 near-Earth objects, and a little over 3,200 of these larger NEOs with diameter bigger than 140 meters. The most important discovery to date is Oumuamua, the first interstellar object discovered in October 2017. I'm just mentioning this as an example of one of the serendipitous discoveries that surveys like Pan-STARRS and Catalina make. So by staring at the sky, we see lots of new things, not just near-Earth objects. This was an unusual object with an elongated shape, with a strong brightness variation, and it accelerated slightly as it moved away from the sun, suggesting that it's possibly behaving a little bit like a comet. I would argue that there are more of these than many other people seem to believe. The reason is that all of our machinery is geared to finding near-Earth objects. So if we were to see an interstellar object one night, look for the next night, we're going to look in the place where it would be if it was a near-Earth object, not necessarily in the place that it would be if it was an interstellar object. I would argue that these things are actually a little bit more common, but just really, really hard to find. Ongoing improvements to Pan-STARRS, mostly we have been finding near-Earth objects using image differencing, but now detection-based imaging has just started to come into use. And I would encourage you to listen to Rob Berrick's presentation on this topic. And we may find that, through the archive that this technique is also very powerful. One caveat as we go into fainter detections is that there will be more strain on follow-up because we'll be trying to follow up fainter objects. We are thinking about some survey strategy changes and planning some simulations using a longer exposure time. We believe that longer exposure times with Pan-STARRS 2 are feasible. We think that they're not feasible with the CCDs that are in Pan-STARRS 1. We're thinking about possibly doubling the exposure time. We would halve the amount of sky coverage, but then we need to decide what directions we should be focusing on. And should we even try to go even deeper, so maybe triple the exposure time, for example. But as we find fainter near-Earth object candidates, the recovery of them and turning them into discoveries will be more challenging. As we move into the era of Rubin Observatory, I would sort of note to everyone that Pan-STARRS currently discovers more than half of its NEOs south of the celestial equator. So that it's clear that in the past, having the two dominant NEO surveys, Pan-STARRS and Catalina in the north, must have led to some systematic bias in discovery space. Pan-STARRS and Rubin will have significant survey overlap regions south of the celestial equator. And it's clear that the two telescopes or two surveys can complement each other by extending the orbits of near objects discovered by each other. So right now, we don't plan any major changes to the survey strategy once Rubin is operational, but we'll kind of adapt as things go. Clearly, Pan-STARRS and Catalina need to continue to survey the northern sky in the areas where Rubin cannot or will not observe. And then finally, I just want to say a little bit about the NEO surveyor mission. So even with help from Rubin, we're not going to get to this 90% of the 140 meter NEOs within 10 years. So the NEO surveyor mission is planned and in development, and we are sort of working with people from that survey to see how we can help. One possibility is that Pan-STARRS will sort of increase its focus in the same direction of the sky where the NEO surveyor mission will look. And then in the middle of the night, continue to work in the opposition, the region of the sky kind of opposite the sun where the NEO surveyor mission is not going to survey. So that's all I have. Thank you.
Thank you very much, Richard. I don't know if it has been said, but the questions will be at not at the end of the whole session, but at the middle of the session for the 7 presenters that are now talking. So we'll wait for all the questions in about an hour. So please stay online if you can, so that you can address the questions directed to you. So the second presentation will be in person. It's modern computational techniques for improving moving object detection pipelines with the Catalina Sky Survey. And we have Carson Fools giving the presentation. Thank you very much.
All right. Thank you all. So today I'm just going to talk about 3 of the most recent improvements we've made to our moving object detection in both survey and follow-up, because we do both of those. Just a little background to get us started at CSS, just so you can kind of get into what I'm going to be discussing. For each field, we produce a ranked list of NEO candidates. So each section of the sky we look at, we have a huge ranked list of candidates. And we have an observer, usually on-site or remote, that's actually reviewing those in real time. So about 10 minutes between the last photon and these candidates getting reviewed. And the way we pick out transients, as opposed to some of the other surveys, is we do source comparison as opposed to image subtraction. And the sources we get are from the source extractor package. So we use those to form our tracklets. So that's the information we use to form those. All right, first new thing to talk about, machine learning classification of these transients. So this work was really inspired by work previously done with the Atlas survey, so thank you very much for the help with this. We started working on neural network classification for these transients that are picked out from the source extractor points. We took these models and trained them on 40 by 40 matrices of the actual pixel values. And we first did this with our 703 Schmidt telescope, our wider field one. And to start with, we just had 3 classifications. These were streak, so that's a clear moving object. Stellar, that could be a moving object or a star, but it's just nice and round. And a diffraction spike, and that's our most common image artifact. So these are what was picked out by our model after running on identified transients. You can see it's doing a pretty good job with streaks. Some of those are definitely streaks. The stellar as well. It's doing a pretty good job of picking out the stars. It does a really good job of discriminating the diffraction spikes. And remember, we were just working with the output from source extractor. Source extractor has no idea what these are. It's just giving you basically magnitudes and positions. So yeah, we incorporate that extra bit of data from the machine learning classification into our moving object detection. And so, like I said, we first started this with our Schmidt telescope. We went back and looked at a month and a half of work, including this new procedure, and it increased number of real detections above our review threshold, 5.2%, which is a huge increase, and that's just by reducing the consideration of the diffraction spikes. So work now is going to be instead increasing the rank of those that are identified as streaks, and also building models for our other survey telescopes. Each model has to be individualized for the telescope. They have quite different image profiles. All right, next thing, we also do a lot of follow-up at Catalina. But we use the same operational software and procedures, the same process as survey to do follow-up. Small differences, these are targeted, and most follow-ups are done tracking at the object's rate. And so we also have a constraint that if we're going for a really dim object, we need a long exposure time. We can't let the stars streak too much because that affects our plate solving ability. So we'll break that into a series of shorter exposures, which we will then stack up. We call that track and stack. And an example of this is here. You can see there's lines of 5 individual stars, so this means 5 sub-exposures were stacked to build up enough signal to detect this NEO. And this is a really good example. The object is clearly discernible, but not too much, so we spent just the right amount of time on this follow-up. However, you might be able to see that there's a potential problem, especially in areas with a lot of background stars. So track and stack will increase the number of background stars, make these objects harder to detect. There's also some effects from incorrectly guessing what the actual rate of the object can be, so we end up stacking on a streak, and it doesn't work as well. This is what that looks like. So this is an area with a lot of background stars, high stellar confusion. Our moving object detection software could not pick out the object. Observers look by eye as well. They cannot pick out the object. So this was an hour of observation time that was wasted. However, we worked with Daniel Parrott, the developer of Tico Tracker, and were able to implement second chance reprocessing. So our observer sees that we failed with our normal attempt. We send the images for reprocessing with synthetic tracking, and within 10 minutes, they get that reprocess field back to be able to check. And then they can say, oh, we found it with synthetic tracking, or no, we still didn't find it. We may need to conduct another observation, try something different. That same field reprocessed with synthetic tracking, the object pops out immediately. We saved an hour of telescope time by being able to reprocess in real time. So far, and this has just been since the last year, we've saved 157 individual follow-up attempts with this method. So the last method I want to talk about is citizen science candidate review. As I said, we produce a ranked list for each individual field of the sky. Our observers review each candidate, and they can only get through about 22 candidates per field, but there are many hundreds of potential candidates that are listed that never get reviewed. We keep it to 22 because A, that's what an observer can manage, and also statistics show by going back and looking at what was actually in the field with looking at pre-covery observations, we capture about 98% of what was in that field within the top 22 candidates. But that still means there's 2% that just don't get reviewed. So to try to get at that 2%, we started a project called the Daily Minor Planet. This is hosted on the Zooniverse platform, and it would not be possible without the pre-existing platform to put it on. There's a screenshot of the web page. This is accessible via web browser on computer, tablet, or phone. There's also iOS and Android apps available. So, like I said, we take the next 22 potential candidates from each field, upload these every night. So these are the previous night's data that's being reviewed. And then we have people actually review them. We take a vote of what people think for each subject, and the ones that are ranked highly, we do a second review and send them in. So far, This project has submitted thousands of observations of main belt asteroids, and that makes people happy. 105 observations of NEOs. Many of those weren't confirmed because of the latency in submission, but it was 4, but 5, because we just got another one last week, have resulted in discovery impacts of new NEOs. So these were bonus. Even more than that, though, the project has engaged almost 9,000 volunteers from around the world in the act of discovery, so on the front lines of planetary defense. And these folks are making over 16 million classifications so far. The volunteers are also actually looking at the image data, so they're alert for any anomalies in it, including this one. So we also inject real known objects into our pipeline to test the ability of the volunteers. This one was a known main belt object, but people said, hey, that looks kind of streaked, looks like they're a tail. They identified this active asteroid. All right, so the takeaways from this collaboration: thank you to the Atlas program. Oh, there's my gong. Thank you to the Zooniverse, and thank you to Daniel Parrott. We're going to continue to look at these modern processes and keep updating our pipeline as well. Please consider citizen science as a way to process more data, but also at the same time increase engagement with this field. Thank you.
Okay, time for the third presentation. We have Larry Deneau here in person, who will talk about NEO surveys doing more with more, optimized scheduling and object search for multi-observatory operations.
Thank you, Marco. Morning, everybody. I'm going to tell you a little bit about the Atlas program and what we're trying to do to squeeze more performance out of our system. Okay. Next. How do I get to the next slide here? Let's see. Green. Oh, there we go. Sorry. Okay, I'm good. Thank you. All right. Oops, back one. Okay. A review of the Atlas system. We just saw 2 presentations by very prolific near-Earth object surveys, and you might ask, why is there another one? And Atlas is different from Pan-STARRS and Catalina in that we have a primary mission of finding objects that are on impacting or near impacting trajectories with the Earth. So we're a last alert system, as we call it. We want to find them right before they hit us, if possible. We've been funded since 2013 by the NASA Near-Earth Objects Program. We started out building 2 telescopes in Hawaii. And after those were working, we asked for funds to build 2 more. And those 2 telescopes, one is up the road at Sutherland Observing Station here in South Africa, and the other one is in Chile. And that was the station that discovered 2024 YR4. Atlas 5 just came online. That's a system that's not funded by NASA, and in fact is funded by the EU. And if you see Javier, go talk to him about his poster, and he'll tell you all about how the Atlas Tede system is getting going. So our systems are wide field. We take 30-second exposures and just tile the sky every night. Unlike Catalina or Pan-STARRS, who has to think about where do they want to observe tonight, for us the answer is always the entire sky, and we just do that as fast as we can. So our typical revisit cadence on the sky is about a little over a day. So to think about how to make Atlas better, we have this cartoon that goes all the way back to the original Atlas concept in 2011 that John Tonry wrote up. And we like to think of this, on the left we have the Earth is the blue dot at the bottom. You can see the circle of the orbit of the moon. And this is a top-down view of the space around the Earth with the sun at the bottom and looking away from the sun going up. And that red shape is a cross-section of inside there where we would be able to detect a 50-meter asteroid. And so imagine that shape being rotated along its long axis, and you have a teardrop-shaped volume, or we call it a candle flame. Inside that candle flame, we can detect a 50-meter NEO. On the right is, if you're at the telescope looking at the sky, that's the density on the sky of where these NEOs might be found. And so for reference again, this is what you might see with a 30-second exposure. For the astronomers out there, that's a sensitivity that goes down to about a visual magnitude of 19.5. And this is for a diameter of 50-meter asteroid, which is pretty close to what YR4 was. So to find more objects, really the only thing we can do is make that candle flame larger. And the main way we can do that is to observe with longer exposures. And so here's that same diagram, but we've bumped up the exposure time to 110 seconds, and that's a number that was carefully selected, and I'll explain why shortly. And so now on the left, you can see two candle flames. The larger one is the volume in which we can see 50-meter objects. It's much larger, and the inside candle flame is what we would have seen with the 30-second exposures. And one takeaway, one important thing about this is this 110-second exposure time was carefully selected so that inside the inner candle flame, those 50-meter asteroids would be brighter, and in fact, they're at around a signal-to-noise of 10 in the 110-second exposures. So normally, we and other surveys like to operate at a signal-to-noise of 5, and when we go from 30 seconds to 110 seconds, those signal-to-noise 5 exposures in the 30-second exposures become signal-to-noise 10 detections in the 110-second exposures. And that's really important, and you'll see that why that is in the next couple of slides. So naively, if we wanted to make our system better, we would just observe for longer and detect more objects and be done. But there are some reasons why we don't want to do that. The first is that it slows us down in covering the sky. So instead of a 1-day cadence, we're now up to a 3 or even 4-day cadence to cover the sky because our exposures are much longer. So we don't want to do that. It also reduces our sensitivity to very small potential impactors because their visibility windows are very short, and we might see them or might not see them if we have a 3-day revisit time or 4-day revisit time on the sky. So what can we do about this? And I'm going to skip this one to avoid the gong and go straight to the punchline. The first is that normally we observe by taking 4 exposures at a footprint on the sky. And for folks in the survey business, that's been the standard for decades. And what we are proposing to do and have demonstrated is possible is to observe with 3 exposures on the sky. At the 5 sigma detection limit, if you recall Carson's pictures of some faint detections, there are many, many false associations you'll make when you work at 5 sigma when you only have 3 exposures instead of 4, but we have a way around that. And what we're going to do is use a software package that was developed by my co-PI, John Tonry, and published in 2023, a way of linking detections across 2 nights where you have only 3 exposures in one night and 3 in the other night. And in fact, we only require that you get 2 out of the 3 in each of the nights. So this thing we call PumaLink, and it's a way of associating these faint detections from one night to the next night at a low sensitivity level and making a discovery. And this, this component where I said that at 110 seconds, the 10 sigma level is where we would have seen exposures from the old 30-second exposures. That means that we can still detect the same objects on the same night using a signal-to-noise 10 cutoff for these exposures that we would have seen with 30 seconds. And so that's the have your cake and eat it too part of this. We don't really lose objects that we can currently discover at 30 seconds, but what we do is we gain objects that we wouldn't have seen at 30 seconds because they're fainter in these 110-second exposures. The second part of this is a change to the way we schedule our telescopes so that we are knowledgeable about what parts of the sky have 3 exposures from a previous night, and we need 3 more to connect them to make a discovery. This is another package that we've developed in-house called ADIOS. It's a tortured acronym for something that I'm not going to explain. But anyway, it's basically a real-time multi-observatory optimizer that can tell you, based on where we've observed in the previous lunation, where is the best place to point your telescope right now to maximize your NEO discovery. And each observatory will ask that of the ADIOS scheduler, where should I go right now, considering where other Atlas telescopes have gone in previous nights, and basically we'll build up our schedule in real time over the night at all of our telescopes. So to wrap up, all of this work is not quite finished. We expect to finish it, the linking part, PumaLink, and the ADIOS scheduler later this year. We're really excited to have the TEDE system come online because that's going to shrink our revisit time even more, and we expect with the 110 second exposure observing time to be able to revisit the sky every 2 days instead of every 4. It's not the same as the little bit over 1 day that we have now, but we think that 2 days is pretty acceptable for finding all of the objects we want, plus the things that are very close to us that have very short observational windows. This technique is adaptable to incorporating other survey data. We've done a pilot project with Catalina to incorporate 703 data from their Schmidt telescope, and the proof of concept worked, and we're going to fold them into this processing. And finally, we think that the audio scheduling service can be a framework for telling or suggesting to other NEO surveys, where can you observe tonight to maximize your NEO discovery rate? So it'll take into account where all of the surveys have gone over recent days and offer to you, if you need, where you can best survey so that the entire system is optimized for NEO discovery. So I'll stop there. Thank you very much.
Thank you. So time for the fourth presentation. Here we have Rainer Kresken. He will be talking about ESA's Planetary Defense Office NEO survey strategy. Rainer, all yours.
Thank you, Marco. Ladies and gentlemen, let me please talk about the NEOCC survey strategy. Before I tell you what we are currently doing, let me tell you about what we are going to do. This is the FlyEye telescope. This is a very innovative, very extremely wide-angle telescope with 1 meter aperture. And before we hopefully start observing with it, we are planning for a first light this summer. We want to make sure we have the opportunity to make all the mistakes and errors that have the opportunity to bog down operations with that telescope. So we have several telescopes running. 2 years ago, all of us were newbies in the field of operating robotic telescope. This is meant to be a fully robotic telescope. So we wanted to get a practical experience with it. So basically, we run 3 telescopes distributed over the globe. We have our favorite telescope, the TBT-1 in Chile, and we have access to several other telescopes across the globe that are operated by other people to give us the opportunity to do follow-up observations. So this is the telescope, the Schmidt telescope at the Caja Observatory on Cala Alto in Andalusia. This is a rather old telescope, but very nicely suited for our purposes. This is an 80 centimeter Schmidt telescope that allows us to do survey work until down to about 22nd magnitude. We are de facto the only user. This is operated by the Caja Observatory, and we are a paying customer here. This works extremely nicely. We have a high efficiency. Unfortunately, the weather used to be quite bad in the last month there. Surprisingly, this is a new feature. This is one of our so-called test bed telescope. Remember, we want to learn how to operate survey telescopes, and the 2 test bed telescopes allow us to do that. So these are relatively small telescopes with an aperture of 0.56 meters. They are custom made, and this is a certain issue. We found that we have plenty of teething problems here to learn about and to resolve, and this is a critical capacity. You need to know all the problems with the telescopes, and you need to learn to handle all these problems. So our workhorse telescope is the TBD-2 at La Silla in the Atacama Desert in Chile, and we have an extremely high gain from this telescope. So we recently opened a bottle of champagne to celebrate the first overcast night of 2025. So you can really rely on getting data every night. We produce about 20 gigabytes of data with these telescopes per night, and we had a steep learning curve to handle all this data tsunami, we call it. So you see, it's technically identical to the TBT-1 at Madrid. The difficulty is that it's rather difficult to access. That means if something breaks, you have technicians on site, but they are not experts with the telescope, so you need to be able to describe problems verbally or in a telecon. we can rely on them being there, but for example, we have significant problems with sometimes getting the data over to Europe, and we need to learn how to handle this. So, as I mentioned before, the fact that these telescopes are custom-made for our purposes brings problems, and when you transfer the data, for example, you need to make sure that everything works nicely. So as I said, we have about 20 gigabytes per night, and we evaluate them with synthetic tracking. Thank you, Daniel Perot. We are using Tycho Tracker as well. We need to make sure that, that all these data end up on time in Europe, and we need to make sure the processing is as fast as possible. We needed to learn how to structure the observations. We needed to make sure that we have, in fact, time to process them also. That means we have 24 hours sharp. If we don't process the data in this given time, we just have to dump data, which is quite frustrating to make place for the new data of the next night to come. And thanks to my colleague Dora Föhring, we have a very good, nicely working processing chain that now allows us, if everything was well, to just finish the data of one night before the data of the next nights are coming in. And so to make all these links work together and to operate everything on time, took a steep learning curve, and we took the opportunity to learn with the telescopes. And after we sort out all the problems with mechanical operations and network connection and stuff, we are now thinking that we are ready to operate the data that we will soon get from the FlyEye telescope that is waiting for us in southern Italy. And I'm ready with my presentation, and I thank you very much for your attention.
Thank you very much. And now the next presentation is Imminent Impactor Discoveries from Hungary, Recent Results and Lessons Learned by Christian Czarnecki.
Hello everyone, my name is Christian Czarnecki from Konkoly Observatory from Hungary. The story of Hungarian minor planet discoveries began in 1936 at the Konkoly Observatory, which was built in the 1920s in the suburbs of Budapest. After the Second World War, the light pollution and air pollution increased in Budapest. Therefore, in the second half of the 1950s, the construction of a mountain station began on Piszkéstető. The first telescope to begin scientific operation in 1962 was a 60-centimeter Schmidt telescope from Carl Zeiss, Jena. This is the same telescope I use today to search for minor planets, and NEOs, of course, significantly refurbished. A systematic search for extragalactic supernovae started immediately, and the most active observer was Miklós Lovas. While his primary interest lay in supernovae, he is also well known for his 5 comets and 1 NEO. It was the first near-Earth object, meteorite Eger. On December 1974, Miklós Lovas recorded a strange streak near the Andromeda Nebula. Several years ago, we made the connection between the mysterious Lovas observations and the famous NEO Phaeton, which was discovered 9 years later using the IRIS infrared satellite. This is a predictory observatory from Phaeton. After more than 3 decades, the photographic plates were retired. We used smaller CCDs between 1997 and 2020. But after 2010s, it was clear that the full advantage of a Schmidt optics must be used to maximize the discovery rate. In 2020, the Schmidt went through the most extensive refurbishment and upgrade. The camera now, our camera now is a black illuminated STA 10 key by 10 key CCD that provide a full imaging area of 9 square degrees. Since the instrument upgrade, the Piszkéstető Neo survey has been using 100% of the Schmidt telescope time. Using the excellent astrometrical softwares, Astrometrica and Tycho Tracker, and the newly developed trail-identified software, NeoDetect, we have discovered 280 designated NEOs in the last 5 years. First, we show the full footprint of the Piszkéstető Neo survey for last 3 years. The 3 by 3 degrees fields are color-coded by the total number of visits. The mid-northern latitude of Piszkéstető explains the dominance to the northern sky. From these results, approximately 10,000 square degree of sky coverage can be expected in the typical year, corresponding to about quarter of the entire sky. Thanks to the new discoveries, Piszkéstető is the most successful NEO discovery sites behind the big US NASA supported surveys. This figure shows the apparent magnitude distribution of our NEO discoveries. Most of these new objects fall between magnitude 18 to 20, with a steep decline towards the faint limit. From the shape of the distribution, one can conclude that our discoveries are close to being complete down to Mag 19.5, while for the fainter targets, we lose the sensitivity quite drastically. A physical more meaningful distribution is that the absolute magnitude. Our survey is most sensitive for targets between approximately 5 to 50 meters. Our faintest discoveries in absolute magnitude are in the meter-sized range. In conclusion, our survey is mostly sensitive to possible Chelyabinsk and Tunguska type impactors, or even smaller objects, thus providing a value service to the global efforts in planetary defense activities. The Piszkéstető Neo survey led to surprising series of imminent impactor discoveries in the past 3 years, but between 2022 and 2024, we identified 3 objects which were successfully tracked prior to atmospheric entry. 2022 EB5 discovered when it was approximately 100,000 kilometers from Earth. Later, the Center for Near-Earth Object Studies at NASA detected the visible radiation from the object atmospheric entry over the Norwegian Sea. They showed that the explosion was more powerful than expected. The 30th largest since measurements began. 2023 CX1 at the time of discovery at a distance at approximately 230,000, twice as EB5 kilometers, and had an apparent magnitude of 19, less than 7 hours prior to atmospheric entry. The CX1 was the 7th asteroid discovered prior to impact with Earth, and the 3rd from which meteorite fragments were successfully recovered. The meteorites found were L5-6 chondrites. Continuing the sequence of pre-impact discoveries, the very small asteroids, 2024 BX1, estimated to be only 50 centimeters in diameter, was detected less than 3 hours before atmospheric entry. BX1 the meteorite of BX1 were classified as rare type obrids. Obrids are linked the Enstatite-rich asteroids, and it is notable that one of their proposed parent bodies, the Eger, was discovered by Miklós Lovas using the same Schmidt telescope. Okay. In all these discoveries, apparent from Lucky, we think the most critical factor was real-time data processing. Since the beginning of the project, we have always planned the data processing so that the analysis of the series of images does not take longer than complete the next series of images. 1 minute, please. People often ask me, especially journalists, what is the secret on the successful of our survey? But I don't think there is any secret or special method. The secret is a large field of view, a lot of work, and always alive, some luck. And finally, I would like to give a special thanks to my family, my daughter and my wife, who have tolerated that Dad has searching news at least 700 nights at last 5 years in remote mode in our living room, at home. Thanks, girls, and thank you for your attention.
Thank you very much. We go on with the following presentation. This one is going to be remote, virtual. It's How Much Warning Time for Asteroid Impacts Will We Have in the Vera Rubin Era by Kathleen Kiker. All yours.
Great, thank you.
We can hear you.
All right, are you able to hear me? Can you see the slides okay?
Yes. Thank you.
Okay. All right, so hello, my name is Kathleen Kiker. I work at the Asteroid Institute, where we build software for astrodynamics and asteroid discovery. And today I'm sharing the results of our simulation of the performance of LSST survey on 30,000 simulated impactors. So as you all probably know, Vera Rubin Observatory, with its legacy survey of space and time, will start collecting data this year. It's predicted to discover 130 NEOs per night in its first year, and could double the total number of known asteroids in its first 6 months. And as some fraction of these is likely to be impactors, we specifically want to look at how LSST does with an impacting population. So first, we generate a realistic synthetic population of impactors with sizes from 40 meters up to 1 kilometer that impact in 10-year bins from 2025 to 2125. These observations were then fed into SORCA, which is Rubin's survey simulator. We take the outputted observations and generate a new orbit for each cumulative night of data, and then calculate the impact probability with each updated state vector with all the previous observations to track the impact probability over time. So these are the results. There's a lot here, but so let's just focus on one set of these bars, first of all. In the colors, you can see the increasing percentage of discovered objects from 40 meters in dark purple to 140 in teal and up to 1 kilometer in yellow. And for this first set of bars, which represents the first 5 years of the survey, you can see there's also those grayed out sections. Those represent objects that were discovered, but only less than 1 year before impact. So the objects were discovered only as they're essentially actively on their way towards hitting the Earth. But you can see as we go out in time, the larger 1,000 meter, 500 meter objects have a pretty high discovery percentage rate, which is great. But as we get down to 140 meter objects and below, we get to below a 50-50 chance of those objects being discovered. And for 40 meters, very much below. So 2 other quick points to note here. I don't know if you can see on the screen, but there's these very slim regions of slightly lighter color. And those are for objects that were discovered but never reached that 1% threshold point. And I think the important thing to note here is that those sections are quite small. So largely, if an object was discovered by Rubin, it would reach 1% impact probability before the end of the survey. And then finally, these whited out sections along the top, those are objects that were observed by LSST, but not discovered based on their criteria of 3 2-observation tracklets over 15 nights. So the main takeaways, Rubin alone, not enough to give warning time for impactors under 500 meters. And many of these impactors, as you can see, these observed but undiscovered represent a fairly large proportion of the undiscovered objects. And then further, if we were to look at how much time we would need for a generous amount of time to launch a deflection mission, if we're being very kind, of course, we see that effective date of warning time pushed out even further, which of course we would expect. Right. So the next question is, for these undiscovered objects, was there any particular population that LSST was likely to struggle with? And we see fairly, so these are the orbital element plots, blue dots representing discovered objects, red and orange representing undiscovered objects, both observed and unobserved. And we see some expected trends with high synodic period objects and those whose orbits are interior to the Earth being least likely to be discovered, is certainly in the 1 kilometer range. And as we get down to 140 meters and below, observability becomes more of a factor, and we see more of the objects not being as observed, with objects with AU 1 to 1.5 AU and semi-major axis being the most likely to be discovered. Okay. So how much warning time are we likely to have? Well, what we really found was that this is mostly dominated by those cases of 0 warning time. So objects that are never discovered. However, if we were to put those aside and just consider objects that LSST did find, for example, for a 140 meter asteroid impacting in 10 years, we would expect an average of about 8 years of warning time. And while we only looked at LSST, so we don't have a baseline to compare this to, this does likely represent a significant increase over what we would expect to have if Rubin was not on the sky. So quickly getting into a few specific cases, here you can see a couple of examples, and to note, all of these are 1 kilometer objects that we're talking about, and all of these orbits, although simulated, do impact the Earth. And so here we have one of those cases where the object is observed but not discovered. So each of these blue dots represent a night of observations. And we can see that this is observed quite a bit, in fact, before and for many years before it reaches this red line, which is where we mark that threshold of discovery of 3 2-observation nights of data within 15 days. So what can we do about this? We took another linking algorithm, Thor, which is able to do singletons, as a baseline, and said, what if we give a more generous linking criteria of 6 observations over at least, or within at least 30 days, extending at least 2 days of arc. And if we do this, then we find that about 40% of the undiscovered objects are now able to be discovered using this more generous criteria. And additionally, the mean warning time would increase as well. And this really just shows the space for which improvements in linking algorithms could show improvement and start eating into that range of undiscovered objects. All right, additionally, twilight asteroids remain an issue. So many of the objects that were never observed at all were ones like this with orbits interior to the Earth. And additionally, many of those who did get observations, but not enough to reach the slavery criterion. Additionally, although it is rare, as I mentioned in the previous slide, some objects do remain with a low impact probability for quite a long time. So this really just underscores the importance of following up each of these objects because, again, these are 1 kilometer objects that have orbits that will impact the Earth. And yet for this one, it remains low impact probability time. All right, and then last one, just we assume perfect recovery. So if there were prior observations, we do take those into account, but that is not guaranteed. I think this object is an example of a case where you might not get those prior observations. And so again, early discovery and investing in recovery efforts are both helpful. All right, so yeah, to conclude, LSST is able to find a large number of impactors, especially over 140 meters. But for smaller objects, it is clear that it alone is not enough to really reach the thresholds that we would like to see. And some things that might help would be twilight surveys, additional instruments for follow-up, and those improvements in both linking and recovery algorithms could all help to close that gap. All right, thank you for your time. Please reach out, and our code is available as well.
Thank you. Thank you very much. Before moving to the next talk, before the question section, I want to point out that on the app, we have a dedicated tab where you can ask your questions, especially if you are online. And it has been activated about 20 minutes ago, so feel free to add your questions for all the speakers so far and the next one to that tab so that we can go through in 10 minutes and ask them to the speakers. Of course, we'll also take some impromptu questions here from the audience online. So last talk before the question break is the 2024 Schweikart Prize winning proposal, the Sunward NEO Surveillance and Early Twilight Detection Sunset Collaboration by Joe De Martini. Thank you very much. And it's also an online presentation. So do we have Joe?
Yeah, can you hear me okay?
Yes, we can hear you and we can see your slides. Thank you.
Just waiting to see my own slides here, but good morning, everybody. It's just about 4 o'clock in the morning in Washington, D.C. here, so excuse me if I'm a little groggy. I am talking today about I'm the inaugural winner of the Schweikart Prize for Planetary Defense here. I don't know if you can see my video, but pretty neat prize here, and it comes with a fancy museum-grade meteorite fragment, so that's kind of awesome. The Schweikart Prize is the first ever International Planetary Defense Prize of its kind, which recognizes graduate students for their innovative ideas and potential leadership in the advancement of planetary defense-related fields. And this doesn't mean just the science of planetary defense or the engineering of it, but they're also looking for innovative proposals in the fields of communications about planetary defense or policy or anything else that you can think of that relates to the field. So it's awarded on an annual basis. The next round of applications were due back in February or March, I think. But if this is something that you or one of your students or colleagues may be interested in, please don't hesitate to apply. It was an outstanding experience. You can see just from this first slide here, I was excited out of my mind to be standing next to Rusty Schweikart himself. But I suppose getting on to my actual proposal here, the innovative idea, I suppose, that I proposed for the first ever Schweikart Prize was the Sunward NEO Surveillance and Early Twilight Detection Collaboration, or the Sunset Collaboration. And the idea behind it was to increase discoveries and improve tracking of near-Earth objects approaching from the sunward detection by way of ground-based twilight observations. So essentially the motivation here was the Chelyabinsk super bolide, which exploded over a small town in Siberia in 2013, as I'm sure everybody here in this room is probably familiar. There were something like 1,500 injuries and over 30 million US dollars worth of property damage just from a small 20-meter object. that was an airburst over the town, so it didn't even reach the ground. And one of the concerns with this object was that we didn't see it until it was already too late for its approach, because it was approaching from the direction of the sun, where we cannot be looking because it'll burn out our optics. So if we go to the next slide, please. Essentially, this is a schematic of, not a true representation, but a schematic of the region of the sky that we can't look because it's obscured by solar brightness on any given night. And if we hit the next slide, please. It's possible to sort of open up the region of the sky that we can see if we observe at twilight time. This is something like 15 minutes to 1 hour just after the sun has set in the evening or just before the sun rises in the morning. So the sun is just below the horizon, and you point your telescope as close to the horizon as you possibly can to try to see those objects that are closer to the sunward direction. So this sort of forms the crux of the kinds of observations that are necessary to see these objects. If we move to the next slide, in my proposal, the main driver for discovery that I proposed to use was the Rubin Observatory. We've just heard here that the Rubin is an incredibly powerful discovery machine for near-Earth objects. And there has been proposed by the community a low solar elongation twilight microsurvey, which should do a fine job of making discoveries or identifying objects in the twilight region, but which can't do everything on its own. And so if we hit the next slide, one of the big parts of the proposal, and the reason that I call it a collaboration, is because we want there to be not just Rubin looking for these things, but as many observatories as possible that are capable of performing twilight observations. And not just observatories, but also amateur observers and anyone else who's capable and willing to point their telescope in the sunward direction at twilight for follow-up characterization. So essentially the idea is Rubin will be looking out every 3 or 4 nights or something and finding everything in the sky that it can, but also looking in these twilight regions. And if it can spot something that can't quite confirm the detection, then this network of other twilight-capable observatories can move in and try to find extra observations and link those together with some of the novel linking software that we've been hearing about earlier in this session here, so that we can try to get confirmed discoveries. Beyond that, if we can involve newer observatories like ATLAS, which is excellent for close approach discovery and warning, and which it's been shown in recent publications is also capable of twilight observations, or the NEO Surveyor mission, or even, as I just heard about yesterday, the NEOMIR mission from ESA, whose primary goal is to look at low solar elongations. If we can link the Sunset follow-up network with these telescopes as well, then it could be outstanding for improving the warning time for these objects. As we know in planetary defense, warning time is really everything. We can't prepare a deflection mission or even prepare an evacuation if we don't know that these things are coming. Let's go ahead and hit the next slide. Just a brief summary. My proposal was the Sunset collaboration to increase discoveries and improve tracking of near-Earth objects approaching from the direction of the sun by way of ground-based twilight observations and performing follow-up mainly with the Rubin Observatory, driving discovery and follow-up characterizations from other twilight-capable observatories and novel orbit refinement software. Last slide, please. I just wanted to thank everybody who helped me on my way to this prize, most importantly, my advisor, Professor Derek Richardson, and all of the folks from the B612 Foundation, who are the organization that grants the prize, in particular, Rusty Schweikert himself and his 2 sons, Randy and Rusty Jr., as well as Colleen Fischetti, Danica Remy, and Delphine Veronice Milan, who helped not only prepare the slides, but get the proposal ready to be put out. Best of luck to the current applicants to the Schweikert Prize. It is an outstanding opportunity to be recognized as a graduate student for work that I have done in planetary defense, potential to advance the field in the future. And I really hope all of you will take the prize very seriously and encourage your students and friends to apply in the future. Thank you very much.
Thank you. Thank you very much for these presentations. And now it's time for a quick Q&A session. I see that some of you have put some questions on the app, so maybe we can start with one or two of them, and then there's also actually questions from the public. We will, sorry? Yeah, the speakers can actually, the ones that are physically here can come to the podium so that they can answer in person. I think we have just enough chairs. There's 5 chairs, 5 speakers in person, so that should work. Okay, while they all sit down, I think we have, seeing the questions now, I think we have a few. The first one, the highest rated one on our app, is for Kathleen. And it's actually very similar to another question that I see down in the app, so we're going to merge them together. For Kathleen, it looks like objects 40 meters and smaller don't have more than a 10% chance of being discovered by LSST. Does this mean that LSST won't practically be able to discover any imminent impactors, which thus far has been all less than 5 meters? Then there's another one that is basically more or less along the same lines. Is it an estimate of how many very small few meter impactors Rubin will find, and how much, with how much notice to compare to the current about a couple per year's rate? So if Kathleen can answer this one, I think it's remotely, but I hope you can hear the question.
Yes, yeah, thank you. Absolutely, and that's a great question. So first of all, we did not look specifically at objects of that small of a category. So we did not look at 5 meters or 1 meter objects. Certainly that's something we could do in the future. Speaking to the 40 meter, so for a planetary defense mine, we had kind of said, you know, if I could share my screen again, I don't know if I'm able to, but going back to that chart, where there was a very small sliver at the bottom. However, there was that grayed out section, which we were kind of saying we don't really care about. That's less than 1 year of warning. But if we're talking about imminent impactors, that comes back in. And in fact, for those smallest objects, were the only objects that we were seeing within the next 5 to 10 years, which is when the survey is active, saw a larger number discovered and then a decrease as time went on, whereas the other larger objects typically saw an increase as time went on. So I think the number is more like around 30% for 40 meters if you're accepting discovery within 1 year of impact and beyond. So still not a lot, and I don't know about smaller objects, but it is actually a little bit better for ones that are impacting imminently than it does for objects, smaller objects impacting 10 or 20 years out into the future.
Okay, thank you. I guess we can, if there's any question here in the room that somebody wants to ask in person, not seeing any hands. I guess we can go on with the next online question. And it's, I'd say for all the survey people here, how much of a problem are the current mega constellations in orbit for NEO detection?
May I answer this?
Sure.
So I basically visually inspect all the data we get. As I said, we do synthetic tracking, but I need to investigate the tracks that Tycho Tracker delivers. And these mega constellations are extremely visible, in particular when the images were taken close to dusk or dawn. But I think they hardly prevent any detection because software is good in just ignoring them. So they are visible, we know they are there, but I think they don't stop us from doing any detection.
Thank you. Is it any different for more traditional surveys that don't do synthetic tracking, maybe?
I would say if you use other techniques than synthetic tracking, then they do have an impact,
yeah,
but I think they are, synthetic tracking is the future, and I think we can cope with this problem.
I can talk about it. So there's 2 potential ways for mega constellations to interfere. One of them would be confusion for near-Earth objects. These are moving way too fast. They're not confused. The second would be, do they obscure enough of the sky to be a problem to cover up potential detections, and also no. They're too small, so no, they're not a problem.
Interesting. So there seems to be a general consensus that they don't do that much for our specific niche of work. Anybody else wants to say anything on this topic?
Yeah, our experience has been pretty much the same as Carson's, which is they're a small nuisance, but have not been the problem that we had all feared years ago.
Thank you. Let's try again. Any other question from the audience here, live? Still no. So we go on with the next online question, which is again for Kathleen. What about the issues with false linkages over the long time span of 15 nights?
Yeah, a great question again. So those are definitely an issue. That's both true for the Thor trackletless algorithm and Rubin's version, which I believe is HaloLink. False linkages are definitely an issue. For this study, we kind of took the criteria as a best case scenario. So if it met the criteria, we considered it discovered or discoverable. And we did not include like false observations in there. But that is a topic that I would be very excited to dive into to apply these in a more realistic way. But yes, false linkages could be an issue.
Okay, we have another question, which is for machine learning training. Can you use the data from other surveys, and can you use the same machine learning model on other surveys? If not, what are the main complications?
So no, you can't directly use the exact same trained model, because that is specific to the image characteristics of your telescoping camera system. However, you can use the same rough design of coming up with classifications of types of image artifacts that are common in your system, collect enough examples of these to train them, and then start using the same architecture for yours. So in that way it is, but I could not just give you the model for 703 and it be of any use to you. You'd have to train your own.
If I can follow up on that, how about the archived? Can you just go back to archival images and use the same training data set to essentially try and find discoveries that might have been missed in the past?
Yes, and that's kind of what we train on. Also, a little nuance. Our camera systems do change slightly over time. As they get older, as the flat fielding changes from night to night. So we do plan on continuously maintaining these machine learning algorithms.
I also have a sub-question on that. How many actual human classified detections did you use for your algorithm?
For each class, approximately 5,000.
5,000, okay, so not that many, not the whole data set that you've ever used, ever gotten with.
Right, I mean, it took a while, but it was a single person working on it for a couple of weeks. It's a human achievable problem.
Okay, interesting. Thank you. I see a question here from Brent.
Yeah, a question for Larry regarding Atlas. And this is sort of related to the online question, but essentially the question is there a point of diminishing returns for building additional telescopes, or are there benefits to building more? Are there plans to build yet more Atlas telescopes?
Thanks. Yeah, no. We do not have plans to build more telescopes. In fact, we didn't plan to build number 5. The opportunity came to us, and we were happy to collaborate with Javier and help them get their system online. It's a completely different optical design. So it's one of these clusters of Celestron ROS 11 CMOS cameras, but it happens to have the same performance characteristics as one of our telescopes. But we found that even with 4 telescopes around the world, we still lack, I would say, enough weather diversity. So we have periods where all 4 telescopes are down for weather. And so a 5th telescope somewhere improves that. And so one is it gives us more weather diversity, and also helps us with our cadence or revisit cadence on the sky, so that we can get closer to visiting the sky every night with our 30-second exposures, or every 2 nights with 110-second exposures.
Thank you. Any other question from the audience? Yes, I see one down there. If somebody can reach the microphone.
So for access to, for pre-discovery, access to pixels across surveys is essential. And while we do have archiving in various capacities, getting more than cutouts is needed because often the line of variations is longer than entire images. And so with WIRE4, we were looking for pre-discoveries, and sometimes the line of variations would be 10 degrees long back in 2018, and we had to manually go find images that intersected those by doing repetitive queries of cutouts from different archives. So I was just wondering, is there a way to better coordinate archiving entire full images, multiple CCDs across entire surveys, such that observers can go grab entire images?
I can speak a little bit to that. I know that we and Catalina, and I think Pan-STARRS is getting started with this, we archive our images with NASA Planetary Data Systems. And so I think most of Catalina's over there now. Correct me if I'm wrong.
No, you're right. We do nightly uploads of the previous night's data, so it's there, full images.
And we're in the process of taking all of our historical data and moving it there as well. So that should be a resource to do, to extract full images or cutouts of any size you want. And also there's the database that can tell you where we pointed in the past.
Just to add to that, the tools for, with NORLab, the issue is you could query a location on the sky, but not the orbit of an object. So adding functionality to search through images based on a fiducial orbit is a nice touch.
So with Atlas, we have a force photometry server that's used for people looking at static, non-moving things. But we've also adapted it to use to work with moving objects. So you can type in the name of an asteroid, and it'll pull out all of the Atlas exposures where that object was and pull out a postage stamp. So it seems to me that it should be pretty easy to adapt that to any other survey that's out there to provide a tool to do that for a moving object.
Regarding the PDS system, their archive has a function called catch, and it can search along the ephemeris for objects that are in those asteroid survey repositories.
Okay, we just got the gong, so I think that's it for the first Q&A session, and we can go on with the other 6 presentations we have in the sessions. Thank you very much to all the speakers for the answers and to all of you for the questions. Thank you.
All right, second part, less observational, more about modeling. Our first speaker will be Federica Spoto. That's a virtual talk. Federica, are you there? Yes.
Yes.
Oh,
I'm
there
here.
she is.
Morning.
Okay, so the title is Minor Planet Center, Updates and New Developments. Take it away.
Thank you, David. Should I share my screen? Do you see my slides? Yes.
Yeah, we
I
should
can
see your
them.
slides, so you should be good.
Yeah, thank you very much. So good morning, everyone. I'm really sad I cannot be there in person this time. I was really looking forward to it, but I'm still happy to give you this presentation about Minor Planet Center updates and new developments. Next slide, please. For those of you who are not very familiar, in case the Minor Planet Center, or MPC, serves as a single worldwide location for tracking and cataloging asteroids, irregular satellites, minor planets, major planets, and comets. And also it's central for all the planetary defense efforts in the sense of we collect the observations, we are sure that the observations and the orbits can go out fast and that can easily accessible. Then the MPC is located in Cambridge, the Center for Astrophysics. We operate as part of the Smithsonian Astrophysical Observatory, and we operate under the mandate of the Division F of the IAA. As I was mentioning, we're responsible for a lot of things. Some of them includes having designating new objects and maintaining a consistent catalog of observations and comets in general for minor planet comets and natural satellites. As you can see in these slides, the MPC grew a lot in the last years. The color code in this table represent the people, like the different tasks the people are working on. So there are like, we are divided into more or less astronomer and software developer. At the moment, the MPC staff is expanded to 16 team members, and we have some recent additions, which are like project manager Paul, and then software developer Iatrik that's just starting in March, and then we have Jorge Hernandez that should start in June or July, but pretty soon, and it's going to be an astronomer. So we're pretty excited that our team was able to grow in the last year. Next slide, please. So what I've been up to, one part would be that each single point of this slide could be a single presentation of an hour long. So I try to summarize everything in just like a short amount of points. But the main idea is that the MPC has spent the last years improving its current systems, and we were working towards getting ready for the large surveys you all have heard about Vera Rubin LSST and NEO Surveyor. So there's been a lot of development and improvement of the current MPC system and new systems around that. Basically, we are trying to improve the reliability and access to our data. That includes the website, mostly around documentation-related pages, to give a better sense to everyone how to access our data, use our data, and like what our plans for the future is going to be. We have been start replicating a lot of database tables to SBN, and then from SBN, they're gonna go out to our users. That should improve the way, the accessibility to the data for example, the large surveys that needs a pretty quick and access to the data. We've been trying to develop more and more APIs. There are a lot of examples on the documentation page, and also, as I was mentioning, the documentation itself. Now, there is a screenshot from the website in which I wanted to highlight two things, like the documentation page and the newsletter page. So under new, there's newsletter. We've been trying to focus also a lot into communicating more with our user, with our community, to try and explain what the MPC is up to, what we've been working on, how to improve in general, like the communication. And the newsletter is one of the things we do. So the newsletters are always available on the website. We also send them out through MPML, and I'm dedicating MPC ML mailing list. The second point, sorry, could you go back to the previous slide? The second point is about virtualization. The idea is that we wanted to create our own cloud system in-house, and that's more or less the image that you can see on the left, on the bottom left of the slide. The goal would have to have a new hardware infrastructure that is all like interconnected, and it's easier. It's going to be very helpful in case of like disaster recovery and faster processing times. And that's where like it's basically based on a lot of virtual machines that run all together. And then the third point is like we've been trying to move all our internal system to a database-centric system, and so that would ensure consistency between flat files and database tables for a very smooth transitions. Next slide, please. The thing I wanted to mention was like what we've been doing on the annual CP recently, so on the annual confirmation page, software in general. One thing that we did is like we created this past impactor page, which is part of the MPC Explorer. For those of you who haven't seen it, the MPC Explorer is going to be a replacement for our old DB search. So in that sense, should contain all the information about minor planets, comets, and satellites. In general, it will contain all the information about designation, observations, orbits, discovery information, and then we are planning to add more information like residuals and everything. And also we have lists. One of the first lists we added is this past impactor. It contains a lot of cool plot if you want to go and check it out. This is a screenshot of the page. Next slide, please. So from the MPC point of view, what is like one of the main issues, or not issues, like problems or like fun stuff to think about when you think about imminent impactor is like when we're planning to designate them. So there's been two different type of approach, which has been like we keep the object on the NSEP as long as we can, or we designate as soon as we can. That means as soon as we have an orbit, which is quite reliable. process, like if you keep it on the NESDP, we know that there are a lot of systems that relies on the NESDP, and then that will help the observer doing the follow-up. The cons is like these objects usually need a designation. So from our point of view, we're trying to find, to work towards like the best possible combination of the two, which is at the moment seems to keep the object on the NUCP as long as we can, but to try and give a designation. So you might see some changes or some tests that are gonna be around that we're gonna try to do in the next like months or whenever a new impactor will come. So the plot on the left, which I always find very interesting, is like a cumulative distribution of the observations we got for every single impactors. This is also available from the MPC Explorer, and in principle is updated every time we get a new impactor. Next slide, please. About that, one interesting thing we've been working on is the NUCP automatic processing, or NAP. So the goal would be like to try and have as less as we can manual processing on NUCP object. And so in that sense, we want to understand when we can actually automate the designation. And this is NAP. This is what NAP is doing. So the idea will be that we want to unpack NEAs and for distant objects have a Q larger than 5.6, please check the latest newsletter because we had some changes on the way in which we're gonna impact distant objects. And also NAP is this automated script that is able to actually automate designate an NUCP object. Now, the thing I want to stress is that before the automation happens, there are a lot of checks that the system go through for every single object to be sure that things are like properly designated. Otherwise, everything goes back to some manual inspection as usual. The work in progress is that we're trying to automate in the designation is very short arc at the moment, so less than 24 hours. At the moment, they are not even touched. And then the fun fact is that 2024 YR4 was actually designated automatically. And then I'll leave you with the last slides, which are thank you. And it contains a plot of all the observations we received in the past year. Thank you very much.
Thank you, Federica. And before moving on to the next speaker, just a reminder for virtual speakers to stick around for the Q&A session, and you can already put your questions down for later. Next speaker is Peter Veres, Machine Learning Improvement of the Near-Earth Object Discovery Process. Peter, are you there?
Yes, can you hear me?
Yep.
Excellent. Good morning from Cambridge, Massachusetts, from the Mind and Planet Center. I'm happy to attend this great conference. Again, I'm sorry I can't be there in person, but let's talk about this little science project I have been working on the last few months, mostly with Richard Clotey. So most of the NEOs in the last 20 years have been discovered thanks to the Near-Earth Object Confirmation page that allows observers to rapidly post their NEO candidates, and then they can be rapidly followed up and also designated. So usually it only takes 1 or 2 days nowadays when a new object is designated to a new NEO. On the other hand, not all NEOCP candidates are NEOs. There could be main builders or other objects. So how do you know which unknown object is a good NEO candidate? So there is a tool that is called Digest2 that has been used almost for 20 years to select a candidate that is very likely an NEO. The score is a quasi-probability score. So basically, if you are close to 100, this number goes from 0 to 100. The probability is almost 100 for an unknown object to be NEO, but the probability drops very sharply. So about 95, the probability is only about 50%. So the Near-Earth Object Confirmation page has been pretty busy in the last 5 or 6 years. So typically we have about 6,000 NEO candidates per year in the last few years. But as I mentioned, not all NEOCP candidates turn out to be NEOs after all, and it's only actually 55% of objects that reach NEOCP are NEOs. And the second most frequent category is main builders or non-NEOs. And the third one is unconfirmed objects. So those are objects that end up on NEOCP, but due to insufficient follow-up, they are not being confirmed. They are lost for a certain amount of time. They can be recovered from archives later, but mostly they aren't. So motivation for our work was to decrease the fraction of unconfirmed objects. So about 11% of objects that reach NEOCP are never found again. And second is to decrease the main belt asteroids that reach NEOCP. So can we do anything about this? And inspiration for this work was another paper we had published last year with Richard, when we used machine learning methods on simulated LSST data to find interstellar objects. So we looked again at the Digest2 score closely, and particularly I mentioned the NEO Digest2 score has been used on NEOCP to distinguish NEOs on non-NEOs as a new candidates, but Digest2 is much more powerful. It actually allows you to compute the probability score for other orbital categories. And there are like 15 of them, and each of them comes in two flavors. One is called raw, one is called no ID. So one is computed with respect to the all solar system synthetic model. The second with respect to the undiscovered part of the solar system. So there are many options that you could use when you compute Digest2 score. So you could ask yourself, what is the probability of an unknown object to belong to Mars crossers, or inner main belt, or Jupiter Trojans, etc., based on the orbital elements you guess for a given short arc. So we studied two behaviors of those tracklets. So we selected the NEOs and the non-NEOs we had on NEOCP in the last 6 years. We divided them into like two categories and computed the Digest2 score for all 15 categories for raw and no ID Digest scores, and look if we can distinguish these two populations, NEOs and non-NEOs. In particular Digest2 scores, we could clearly see there is a distinct behavior. For instance, if you look at the Trojans Digest scores, for NEOs and non-NEOs, you could see like NEOs Trojan Digest score is pretty much always 0, but for non-NEOs, it could be non-zero. So you could immediately use this score to distinguish NEOs and non-NEOs. So in so-called basic filters, we try to select non-NEOs on NEOCP, depending on how many NEOs can you sacrifice in those 5 years. So we selected filters called filter 0, filter 1, and filter 2, based on how many NEOs can you lose at most in every single Digest2 categories. And let's see, so if we select filter 0, we can eliminate 12% of non-NEOs on NEOCP for the cost of losing 0 NEOs. Filter 2 allows you to eliminate 21% of main belters for the cost of 14 NEOs in 5 years. That's not a lot if you have about 3,000 NEO discoveries per year. So in the next step, we look into the machine learning that is the main driver for this work, and we actually studied 4 different machine learning methods: the gradient boosting machine, random forest, stochastic gradient descent, and neural networks. And we used the 4 years of data as a learning sample, and the last year of 2024 as a validation set to use what we learned. So the results from the machine learning are quite promising. So the precision for NEOs is about 98%, and precision for non-NEOs about 82 to 85%. So these are the confusion matrices for our machine learning method on NEOs and non-NEOs on NEOCP. So the upper left corner is always for true positives for NEOs. There are more than 3,000 in 2024 that have been identified correctly. So we looked closely at the SGD model that has the lowest number of misclassified NEOs, 189. So just to conclude my talk, what we have done with these machine learning methods. So our basic filter is about to remove from like 12 to 20% of non-NEOs from NEOCP for a little to no cost of losing NEOs if we use it on arriving NEO tracklets. If we use machine learning on incoming tracklets to NEOCP, we could correctly identify 95% of NEOs and 85% of non-NEOs. Of course, that comes with the downside of losing 189 NEOs per year, let's say in 2024. So you may think losing that large number of NEOs is a tragedy, but not necessarily, because when you apply this machine learning on their follow-up tracklets or tracklets of the same objects that were misclassified later, a vast majority of them are again classified correctly with machine learning. So we are left with only, let's say, about 41 out of 3,000 that we lose on NEOCP. If we use machine learning, but at the same time, we will eliminate almost all non-NEOs. So hopefully, if this is applied in one day on NEOCP, we will save a lot of observing time that will allow observers to forgo for objects that we lose, like 11% of them, and you can save a lot of follow-up time. So we even broaden the numbers, how many pointings would be saved if the non-NEOs are not posted on NEOCP. So at the end, it's just a balance between sacrificing a small number of NEOs per year and elimination of most of the NEOs. Thank you.
Thank you, Peter. We're going to move on to the next speaker. That's Rob Warwick, identifying potential NEOs based on their single tracklet motion. Rob, ready to go?
Yeah, just a second. Can you see my slides?
Yes, but they're not full screen.
All right, that should be good.
Yes.
All right, so I'm going to talk about identifying potential NEOs based on their single tracklet motion. Sec. So the goal is to increase the NEO discovery rate by searching for objects which you might not otherwise found. As Peter summarized, there's the Digest 2 score. So this gives you a numerical score between 0 and 100. It classifies objects based on its motion. And if it exceeds 65 for your discovery tracklet, then it can be posted to the NEO confirmation page. However, you can get NEOs that are less than this score, which may actually prevent you from realizing their NEOs and following them up. So basically, there's NEOs that can be hidden in plain sight. So there's really two techniques that we can apply. The first is multi-night tracklet linking from the isolated tracklet file. So I've talked at previous PDCs on this aspect of it. With that linking, so far to date, we found just over 100 new NEOs based on lower score tracklet in the ITF file. However, today we're going to focus on single night detections, looking at the motion in an individual tracklet to see how it deviates from being linear. So these suggest, but are not completely guaranteed, that the object is very close to the observer. So tracklet curvature itself, what is it? Well, quite simply, it's when your tracklet appears to curve with respect to the great motion that it might otherwise have. So you can imagine that if you drew the line representing the great circle, it'll basically go from one side of the line to the other and then back. And in some cases, you can actually notice this directly in the images. It is a good indicator for an object being close to the Earth, but there are some non-NEOs that also show an amount of curvature. And there's really two ways to compute this curvature. There's cross-track and a long track. We've really focused on the cross-track curvature amount. Usually cross-track residuals are smaller than a long-track residuals, especially for trailed objects. So that's really what we focus on. But we do fit the motion for both in our work. You can get an idea of curvature with having at least 3 detections. However, if you have at least 4, then you can get an idea of what the uncertainty is in your tracklet curvature, which lets you be more confident if something truly is a curving object. The one object that kind of really kicked off the interest for us ended up being known as 2020 SO. So this actually appeared in our data review as a Digest score 1 object, but it had a really large residual. So the residual was about 5-6 times larger than what a typical tracklet would have, but the detection images look perfectly okay. So when this was found, we actually force posted it to the NEOCP. We identified some recoveries in Pan-STARRS images, and it received additional follow-up, and it was designated as 2020 SO. Now, it was actually turned out that this was an artificial object. It was the upper stage Centaur from the Surveyor 2 spacecraft launch. So the MPEG was eventually deleted, But it does show that objects that are very close to the Earth can indeed exist with very, very low score. So had this curvature in this object not been noticed, this tracklet would have just been placed in the ITF, and whether it received follow-up is another question. So in terms of automatically searching through the isolated tracklet file, so we have a routine that every day it downloads all the recent tracklets added to the ITF. It sorts through them and computes the curvature terms, and it sends us an automated alert seeing if there's any potential candidates. Now, for potential candidates, we can either look for recovery images, or we can just post them directly to the NeoCP, which allows for additional follow-up. We found about every 2 weeks at a very non-strict criteria we could get a trigger. Most of the PS cases were actually rejected. So one thing with pan-stars is currently we only submit uncertainties for objects that end up on the NeoCP. So the vast majority of ITF tracklets from pan-stars don't have any uncertainties. So this kind of limits the complete accuracy of our curvature measurements. Otherwise, as we get candidates, we can post them to the NeoCP. One Catalina object was noticed. It had significant curvature in the images, so that was confirmed. It ended up not being an NEO, but it was a good test case for us. A better example was P11 TUGX. So this was actually a relatively slow-moving object. It was quite bright, and it had very obvious curvature. When asking the MPC to post it, Dave Bell actually noticed that it was interesting that the digest is only 6, but the variant orbits on the NeoCP are 96% NEO-like. The actual curvature term, if we remeasured the positions, we could actually fit it quite accurately. So it was very obviously an object with curvature. Unfortunately, we weren't able to actually confirm this due to a lack of follow-up. So one lesson from this is it is good to analyze ITF tracklets soon after they're submitted. Using the MPC SPN database, the tracklets can be obtained quite quickly. And for pan-stars, we really need to better understand uncertainties for non-NEO submissions. So we haven't had very many. Perhaps this is expected. So, objects closer to the Earth, you'd probably expect them to have much larger score. This is confirmed by the multi-night tracklet linking. If we look at a distribution of ITF designated NEOs in terms of their perihelion distance, the majority of them are up near the 1.3 AU limit. So this does suggest that most of the objects that are found in the ITF at lower score are not as close to the Earth as you might think they are. However, there is some bias. So having the curvature, especially as the case for 2020 SO, it does kind of artificially inflate the residual because the great circle residual is assuming linear motion. So really, same-night follow-up is the only really way to confirm these objects. However, one improvement we've been making in pan-stars now is we've recently begun to process what are called chip images. So the traditional pan-stars detection uses difference images, so it operates on a pixel level. So we're focusing now on chip-level images. So these take the individual images, a source extractor type program is run on them, and we use all the individual detections to link tracklets. Now, one obviously problem with this is there are a lot of stationary objects in the catalogs. We remove these by considering all the other exposures that have been taken in the past with pan-stars that overlap this exposure. So we combine 100 images, all W-band, very high quality, and every object that is consistently at the same location in all of these images is removed. The image on the left here shows an example of a catalog from a single exposure. You can notice the CCD structure of the pan-star chip. Along the right side where it's denser, that doesn't have any source extraction done, or the background subtraction done. So you can see it does have a significant effect. There are some other benefits to this study. So there's a huge increase in signal-to-noise ratio, which will improve the accuracy of finding object with curvature. The other thing we can do is we can actually make our tracklet linking algorithm very curvature aware. This gives us much more realistic GCRs to find objects. Another important benefit is objects like 2019 OK, they should be detectable through this kind of analysis. So some initial results, we've had some objects on the NEO-CP. There's really two recent types that I want to say. So one of these had very obvious curvature. Unfortunately, it wasn't followed up. Two other ones actually had 2019 OK style motion. Using Scout, we tried to follow these up at CFHT. If they were very boring objects, they should have been located exactly where Scout said they were. We didn't find them. So I'm not claiming these are close approaches like 2019 OK, but rather that our new method is actually sensitive to these types of objects. I'll just put the summary slide up for you to read here. Thank you.
Thank you, Rob. Let's move on to the next speaker, also virtual. That's going to be Gonzalo Tancredi. How many 1 kilometer NEAs are there? A critical revision of different estimates. Gonzalo, are you ready?
Yeah, ready. Shall I share my screen?
Yes.
Okay.
We can see the slide. You can go full screen.
Yep.
Okay, all good.
That's okay. Okay, well, I'm sending my greetings just from the other side of the Atlantic Ocean. I would ask you not to make a big tsunami if you have an impact, because it will be directly to us. The second thing is that my apologies for not being able to attend this PDC. I have recently assumed some political duties. I have become the National Director of Science and Technology in my country, and that's a big task. So I was not able to attend, although I was willing to attend this PDC, the first one in the Southern Hemisphere, since for many PDCs, only Duncan Steele and myself were the only attendants from the Southern Hemisphere. So going to my presentation, the question is, how many dangerous asteroids could potentially hit the Earth? That's a typical question from the public and the media. And usually we say that this number is size dependent. And the community has agreed in two limits, that 1 kilometer objects are responsible for global catastrophes, and 140 meter objects for regional events. So we answer that question usually giving numbers for those limits. In the recent years, let's say in the 25 last years, there have been many estimates of the number of NEAs that we would expect to find. These numbers are listed here, at least these 15 different papers. And if you look into the table where you have the number, they usually agree in the range of 1,000 NEAs larger than 1 kilometer. But most of these estimates are based on an estimate of the age of the actual magnitude on the order of 18 or 1775, and assuming a constant albedo, although there are some estimates that take into account the albedo distribution. So the consensus is there are roughly 1,000 NEAs larger than 1 kilometer, but the estimates range from 770 to 1,500. Most recent estimate concentrates in the range from 800 to 1,000. But my idea is to do a critical revision of this consensus. So first, I look into the discoveries per different age range, and you can see in the left the differential number of discoveries, so the number of discoveries per year, and in the right, the cumulative. So if you look into age values less than 18 or even less than 20, you can see that the discovery rate has a peak maybe in the early 2000, and then it's decreasing. And therefore, the number of NEAs, the cumulative number, is getting pretty constant. So what I have done is to try to extrapolate this tendency of discovery in the future. And for doing that, I use a cumulative gamma distribution. I don't have time to go into detail, but this is use of this function is justified with some simulations. So in case that the discovery frequency low and it's almost, let's say, it's decreasing in the last year, these estimates are quite good. And for example, if we take the age less than 18, what we can see is that the number will not increase too much, and maybe we are reaching over 90% or 95% of the population. In particular, if we take the limit of 17.75, we have already something like 868 objects already discovered. The estimated number would be in total 874. So there is almost 99% of completeness. Nevertheless, the latest estimate of this population is on the order, for example, Harrison showed us 2021, 940, and next morning, presently 936. So it seems that there is, looking to these estimates, there is a number of on the order of 60, 70 missing eons. So the question is, where are those missing eons? If these estimates are correct, or the alternative is that those estimates slightly overestimate the real number. So if we use the limit of 75.75, well, then this limit of the order 900, let's say, it's reasonable. But then the problem is that from the planetary defense perspective, we are interested in limits based on size and not on age. So the problem is how to convert age into size or how to make an estimate on. And the problem that we have is that the relation between absolute magnitude, diameter, and albedo, it's a tricky one. It's not a linear relation. And these relations are shown here are clearly highly nonlinear. So if we look into the albedo distribution of the NeoWise database, we have these two plots. One in the left, it's the linear plot. In the right, the albedo is in the logarithm. And you can see that the albedo distribution of NeoWise observations, it has something like a bimodal distribution. And in particular, you can see it clearly here in this histogram and in this variation with diameter. In the histogram, you can see that the albedo distribution, it's a bimodal. And if you use the mean or the median, you are not considering the squeezedness or the bimodal characteristic of the distribution. But in addition, if you look into the right plot where you have the albedo values as a function of diameter, you can see that there is not very much difference between different diameters. So the albedo distribution is pretty constant regarding the diameter. So this is a plot of the absolute magnitude versus diameter, because NeoWise was able to make an estimate of the diameter directly from the observation and from some thermo models. And also you have the values for the different albedos for these diameters. So the problem is that NeoWise has only a few, I think something like 15 or 1600 observations, but nowadays we have much more, many NEAs already discovered. So what I have done is to make a simulation of the diameter estimated from age values using the nearest neighbor resampling method. So the idea is I take the age values from the MPC and make a guess of the D values, of the diameter values, using the NeoWise data and this resampling, nearest neighbor resampling method. I don't have time to go into detail into this method. So if I use this, then I can make now estimates of the evolution of the discovery rate of these of NEAs, but now based on diameter. And what we can see that, okay, we still have this tendency that with, for example, diameters greater than 1 kilometer, the discovery is going down. But what it's interesting is that the estimate that they have for the numbers of NEAs larger than 1 kilometer is much larger than the previous estimate. I'm making an estimate of the order of 17 750 NIAs larger than 1 kilometer, and a completeness of 87%. So in order to resume, these are more of the numbers. The number of NIAs larger than 1 kilometer on the order of 1,700. And the conclusions are that, well, although the previous estimates of NIAs based on the H value and converted to a D value, it's on the order of 1,000. These estimates are giving numbers much larger, and that's something that, well, I'm still working because then it would have consequence on the impact frequency. And just to end, I would like to acknowledge my son. This is my first time that I have worked with my son because he has graduated in statistics recently, and he has helped me a lot in this for this presentation.
Thank you, Gonzalo. Let's move on to the next speaker. Believe it or not, this one is in person. Mark Boslow, 2032 and 2036 risk enhancement from NEOs in the Taurid stream.
Thanks, Davide. So yesterday I encouraged everyone to question our assumptions associated with the consequence part of the risk equation, just due mainly to the sparse and limited validation examples, but also to the epistemic uncertainty, which is really difficult to evaluate. And today I'm going to ask you to question the probability part of the equation. So let's see, there we go. So here are the assumptions that I want to talk about. First, risk assessment for planetary defense implicitly assumes that impacts are random, and we know that's not necessarily true. The best example is the difference between sporadic meteors and meteor showers. So those are tiny, mostly little dust-sized particles, but why would we think that bigger things, Tunguska-sized objects, don't also follow streams? And they just haven't been observed very much in space. So risk, the way we define risk is really just the integrated product of probability and consequences over size. So you basically add up all the possibilities, and the probability of that thing happening times the consequence of it happening. So if events are truly random, then probability is constant. It doesn't change with time. But if events are not random, then the probability can change with time, and we can when we do that integration, we do that sum, we can consider that to be a coherent risk. It increases and decreases as Earth perhaps passes through these streams. So actual risk can be a combination of coherent and stochastic risk, and that ratio can change with time. So going back, way back to Shoemaker, it was kind of implicit in his review article way back in 1983, before the term NEO was coined, before the term planetary defense was coined. And this article was not about planetary defense, although he was concerned with risk. It was primarily about explaining the frequency of impacts on Earth. Gene was a geologist. He was interested in impacts on Earth. And so, he basically built into his graph, and this is the first example of this graph that we now use, a version of this graph that is sort of kept up to date by Al Harris. But there was almost zero survey data at the time. There was just a handful, a few dozen objects in Earth-crossing orbits that had been found at that time. So he basically was using craters on the moon to estimate the probability of events, and he was labeling the events, with arrows pointing to his best curve. He was, defining what is the average impact interval. Well, as soon as you start talking about average impact interval, people are sort of going to assume that there's randomness associated with that. And then a decade later, Chapman and Morrison really published the first probabilistic risk assessment for NEO risk. And this has kind of been baked into the way we think about things. And they took Gene's list of arrows and impact interval and put it on one of the axes of this plot. But again, it's a pretty sparse plot. Surveys were just really starting to ramp up in part due to this paper, the Space Guard surveys. So this is a recent version of the Harris graph, and it's got astronomical survey data that's inferred from how complete the survey is. And it's also, he's got a constant power law line on there, and there's a deficit by, this is a log-log plot over many orders of magnitude. That's an order of magnitude deficit in the open circles for Al's estimate of how many of these objects there actually are. But if you look in the upper left-hand side, you can see other symbols. Those are objects that have hit the atmosphere, and those way outpace the inferred population based on this stochastic assumption. And if you look, there's symbols for Chelyabinsk, Tunguska, and there's a little infrasound red triangle between those. That is a huge event that we've kind of ignored. That's actually a South African event. That happened in the Southern Ocean between here and Antarctica near the Prince Edward Islands. And this is from Silber et al., a paper that came out a few years ago. Doug Revelle found that it's in 2 infrasound stations. There's, again, sparse data, but the approximate yield that Doug estimated was 900 kilotons, bigger than Chelyabinsk. But if you look at the frequency of those, it way outpaces what you would expect based on Al Harris's astronomical estimate of population. That implies that there is a coherent component. So this is a paper that was published in 78. Oh, okay, sorry. This paper was published in 78. Kretzak speculated that Tunguska was a fragment of Comet Encke in the Taurid stream. So there's a Taurid meteor stream. It's got an orbital period of about 3.4 years. And let's see, here's his diagram of the orbit of that stream intersecting the orbit of the Earth. And so my only real role in this work is modeling the Tunguska impact. So I did a family of simulations showing the pattern of peak pressure or peak dynamic pressure as a function of entry angle, elevation angle of the entry. And the one that matches the tree fall pattern, the observed tree fall pattern, the best is about 35 degrees from horizontal entry. And I repeated this based on the assumption that it was a Taurid. So if it was a Taurid, we would know the entry angle was 32 degrees. We know the azimuth at that time of day, at that location, on that day of the year. And so I did a couple examples, 5 megatons on the right, 15 megatons on the left. Depending on your assumptions of how hard it is to blow down trees, they both pretty much match the shape of the Longo map in the middle. So here is a simulation from University of Western Ontario. This is based on just assumptions of basically a distribution of objects in this Taurid stream, and there was a survey at the Canada-France Hawaii telescope on Mauna Kea, and then the sort of polyhedron there is the volume of the observable volume. And I'm going to show a quick movie, if it plays. There we go. So this shows a 2032 encounter with this swarm, and it turns out that 2032, so it's coming in, so this is the first node pre-perihelion pass. So these are small, if these are small Tunguska-sized objects, they linger most of the time way out past Mars. They're not observable astronomically, and since we started the Space Guard survey and the Georgie Brown survey, these haven't been the subject of there hadn't been targeted surveys till 2022. So the targeted surveys did show that there are some Tunguska-sized objects in this, more than would be expected, assuming completely random populations. And so, since I'm being gonged off the stage, I will just leave my conclusions up.
All right, thank you, Mark. And our last speaker is Paul Abel. Predicted discovery of low delta V targets among the NEO population by NEO surveyor. Hi, Paul.
Hello, can you hear me?
Yes, we can hear you, and we can see your slides. Feel free to go full screen.
You should be full screen now.
It's not.
It should be full screen. How's that?
Not yet. Maybe there is a lag. Well, I'd say just get going. Yeah, they're not full screen yet, but we can probably see well enough, so why don't you just go ahead.
Okay, I'm not sure why it's not full screen. But anyway, I just wanted to talk to you a little bit about the NEO surveyor and some of the low delta V targets that it might see. Okay, basically a little bit about NEO surveyor, obviously looking for NEOs before they find us. This is a mission that's designed to find, catalog, and characterize NEOs. This mission responds directly to the 2005 Georgie Brown survey goal that requires NASA to find 90% of NEOs larger than 140 meters in diameter. That's supposed to be within 15 years of the enactment of the law, 2005, so hopefully before the end of 2020. We're a little bit behind that, but as Lindley said on Monday, we're looking to launch this system in September of 2027. It's an infrared space telescope with a design and survey strategies to optimize for discovering the NEOs that are most likely to impact the Earth.
We don't see the slides changing, so we might have to try these again. And I don't know if we can share them from here.
All right. Try.
Yeah. Now we can see. There's slide number 2.
Nah, just go ahead and try and.
Okay, it's working now. I think they're sharing it from here. So just call when we need to switch to the next slide, and we should be good.
Okay, you can see this. Yeah. Okay, let's do that. Apologies, there's thunderstorms here, so maybe the bandwidth is not good. So basically, if you can hit the next one again. Yeah, okay, great. So why do you want to do this now? Obviously, because you want to have a lot of time to think about something. You see something coming, you want to have lots of warning time, and the mitigation is more effective when you have years to decades to plan. Roughly, we have 40% to 45% of this 140-meter population that has been discovered to date. On the right-hand side there, show a pie chart of the sort of not found to found ratio. The total population is estimated to be about 25,000, so it sort of gives you an idea. This is status of the survey as of the end of last year. And current surveys, actually go back please. Current surveys are not going to reach this level of getting to the George E. Brown goal of 90% of the 140 meters for many decades. So looking at more than 30 years in advance. Next, please. So here we have the mission. You can go next. This is the mission architecture. This is an observatory. It's going to survey from the Sun-Earth L1 in a halo orbit. So Sun-Earth L1 is just an interior, the point interior from the Sun between the Earth. This is a telescope. It's a 50-centimeter telescope. It observes in 2 infrared channels, imaging simultaneously. One channel is 4 to 5.2 microns, and the other one is 6 to 10 microns. Has a large field of view. It's 11 square degrees, so it covers a lot of sky. The spacecraft has got good heritage. It's a 3-axis stabilized, and the only deployment is the ejectable cover that comes off. Next, please. So we have created a survey simulator to predict how many asteroids and comets we'll see with NEO Surveyor. It uses a reference model population of small bodies along with a model of the observatory, the concept of operations of the mission, and the detection capabilities to calculate how many objects, both asteroids and comets, will appear in each visit, and then of that, how many objects will be detected. The model includes NEOs down to 30 meters, comets, and also background objects such as main belt asteroids and Jovian Trojans. With the completion of the mission, hopefully 10 to 12 years, we're going to find upwards of 200,000 to 300,000 new NEOs, millions of main belt objects, and thousands of comets. So this is going to be really revolutionizing our understanding of the solar system and understanding what's in our backyard. Next, please. So this is a plot. You can go again, just hit a couple more slides. So basically this shows looking down on the solar system, this is a simulation that was done based on a 5-year survey, detecting PHAs, those are the blue dots. They are defined as having a minimum orbit intersection distance equal to or less than 0.05 AU and diameters greater than 50 meters. You can see in the grayed out zone there, the NEO Surveyor field of regard. Compare that to the NEOWISE field of regard, and then of course the ground-based surveys field of regard. So NEO Surveyor observes at lower solar elongations and is able to pick up some of those objects, a lot of those objects in the very Earth-like orbits, which is different than the ground-based surveys, which have to operate at nighttime and look more towards the opposition side. Next, please. So because it has the ability to observe close to the sun, this really helps us detect objects in very light Earth-like orbits. These objects tend to have the lowest minimum orbit intersection distances and pose the greatest risks to Earth. NEOs on these Earth-like orbits are more difficult to deflect, all things being equal. And this attribute of NEO Surveyor's operation, obviously it's vitally important for planetary defense, but I also point out that it provides an opportunity to identify low delta V mission targets. Next, please. So this is a test. We did a simulation for a 10-year sim versus known NHATS. So NHATS is the NASA Human Spaceflight Accessible Target Study. I leave the link there at the bottom. People can go to it. And this is a study that's done with 6,100 NEOs. Assumed diameters are based on albedo of about 14%, and you computed completeness. So basically, you look on there. I've highlighted two spots. So the results for NEO Surveyor in this 10-year simulation, it's 98% complete down to 100 meters. So it's very effective, and then 50% complete down to 30 meters. Note the simulation was cut off at a 20-meter size range. So this shows you the power of NEO Surveyor. Next, what we also did is looking at the NHATS-like population, but with 50 to 140 meters. Keep in mind that NEO Surveyor is optimized for 140 meters and up. but we wanted to look at the 50 to 140 meter population. So we used 10,000 small synthetic NEOs within this diameter range, and we matched the NHATS population in terms of the orbital elements and the moids. And what you can see on the chart here, if you look at the NHATS, like it's 45% complete in this population. The regular NEO background is in this size population is 28%. These numbers sort of jive with the NHATS only simulation. One of the things I would also like to point out is that 10% of this population, of the NHATS population, are expected to be found by other surveys. Next, please. So why is it so good at finding targets? Well, it's because these objects must cross the orbit of the Earth, and low moid objects, but low inclination and low eccentricity objects spend more time near the orbit of the Earth. So this plot here is now a little different. It shows the results for 140 meter and larger NEOs, and basically the effectiveness based on by moid. So if you go and hit the next couple of arrows here, you can see that basically when you're looking for moids down to 0.01, you're at 92% complete. Down to 0.1, you're at 90% complete, and then all NEOs in this 140 meter bigger, you're about 86% complete. Next, please. Yeah, those are the arrows coming in. Okay, so go back. There you go. This is conclusions, just to sum up. Yeah, go back. Very well suited to detect near-Earth objects in very Earth-like orbits. In addition to the planetary defense benefits, it also provides this great opportunity to identify low delta V mission targets. And I'd like to point out this is a really foundational asset, because not only is this vital to the planetary defense community, but also of interest to the science institute, resource utilization, and exploration communities as well. And with that, I stop, and thank you very much.
All right, thank you, Paul. And we now have time for a Q&A session. Mark, if you want to come back here, I'll keep you company. And we have all the other speakers online. And I guess we can either ask questions directly here from the room, or just go and read the questions from the app. I'll start from the app, but feel free to step up and ask questions as you see fit. For Federica, the first one: will there be a way to access MPC Explorer through API or a similar functionality?
Hi, yeah, thank you for the question. Sorry, my video said I can. I'm not unable to start the video because it's been disabled by the host, so that's why I'm not on the video. But other than that. Yeah, thank you for the question. Yes, actually, this is possible. And every single page in the MPC Explorer is actually, it runs from an API, and it's the same API that's been created for the community. So in the documentation page, there are information on how to use every single API. And so there is the one for the observations, orbits, NUCP observations. And then the more services we add, the more you will you see, different APIs.
Okay, thank you, Federica. Anybody from the room?
Yes.
Oh,
Hi.
Gerbs.
Yes. Hi. Gerbs Bauer, University of Maryland. I have a question for Gonzalo. Gonzalo, what happens, or do you have an idea of what may happen when you consider the comet, the NEC population? How that would influence your statistics?
If you look into the different models for the distribution of NEOs, near Earth objects, including asteroids and comets, you see that the contribution of comets are very small. Generally, there are much less comets in NEO orbits than asteroids. So I don't think it will affect too much.
And that remains true for large, 1 kilometer or larger?
Well, you know that 1 kilometer comet at 1 AU will be a very bright object unless it's very inactive. So one would expect that near-Earth comet would have an increase in magnitude, maybe 2 or 3 magnitudes compared to bare asteroid. So I think that for NEAs larger than 1 kilometer, we are already reaching the limit. The discovery rate it's very low nowadays, and because we are able to detect almost any object that is coming closer to 1 AU from us. So in the case of comet, it will be even better because it will be brighter than a comparable NEA.
Okay, so next question is for Mark. Could we test your prediction about 2032 and 2036 with more observations now?
Yeah, thanks for the question. I should say this isn't really my prediction, and you know, I didn't really have enough time to go into the details, but this is from David Asher, who, with Victor Klube in 1993, wrote a paper proposing coherent catastrophism and proposing that there was a resonant swarm, so that these objects, which came from Comet Encke, are in a 7-to-2 resonance, mean motion resonance with Jupiter. So every 2 Jupiter orbits, it makes 7 orbits and lines up at aphelion with Jupiter. And I don't fully understand the dynamics, but that keeps the swarm together. But the swarm is very diffuse, and it's something like plus or minus 30 degrees of mean anomaly wide whenever it comes into the inner solar system. And so that swarm passes Earth within that plus or minus 30 degrees fairly often, and there will be opportunities between now and 2032 and 2036. What's significant about 2032 and 26 and 2036 is that according to Asher, there is the concentration is much greater towards the center, and the delta mean anomaly in those 2 years is only 1 degree, and that happens every 61 years. The last time it happened was in 1975, and there was a lot of seismic activity on the moon that can only have come from bombardment of objects and it happened right at the time of the Torrid Swarm passage, the hypothetical Torrid Swarm, which I think there is evidence that it does exist.
Okay. Question?
Hi, Gonzalo. Very nice talk. Do you expect a similar effect on smaller populations, for example, in the impact rate of PHAs or even smaller asteroids?
Well, yes, because this albedo distribution is very similar in all the diameter range. So the problem here is that since this relation between diameter, albedo, and age is not a linear one, then if you use a mean, you are not including the squeezeness of the distribution. So in particular, you are not including the low albedo objects with a similar weight as you are including the high albedo ones. So if this bimodal distribution, that it looks to be the same for all the different size range affects, it will affect not only the objects larger than 1 kilometer, but also the object with 140 meters, larger than 140 meters. The problem that for these small populations, we are far from reaching the completeness. So it's difficult to make an extrapolation for what would be the numbers. So up to now, we can only give some kind of lower limit for these numbers with this model.
Okay. So next question for Peter. You talked about the balance between cleaning up the NEOCP but maximizing the rate of NEO candidates. And the question is, isn't it more important to maximize NEO candidates than minimize MBAs?
It is, but on the other hand, this work and the previous work show that most of those 11% of objects not confirmed are likely NEOs. So we are losing 600 candidates per year. So if we can decrease the non-NEOs from NEOCP observers, we'll have more time for the follow-up. So I assume it's much more easier for the follow-up observers to go for slower targets that are non-NEOs. And of course, it's much more difficult to hunt for those fast ones that have large uncertainties. And the observers are often motivated to get their name onto the Minor Planet Electronic Circular as a follow-up observer. So they will prioritize easier targets. So if easier targets are not on NEOCP and those are main filters, then it would probably better to have, let's say, 300 more NEOs from those unconfirmed that losing a few dozen NEOs. And there was a second question that was kind of related. What kind of objects do we lose with machine learning? Those are usually semi-large AMORs, so kind of more distant objects, not the closed ones or impactors.
Okay, thank you. And we're out of time, so let's thank our speakers again. That concludes the session, and I don't know if there is a last-minute announcement or not for coffee break. No? Okay.
No, thank you, Davide and Marco. Sorry. No, just want to send you to the coffee break. We're a little bit short on time, so please, 35. That's 10 minutes, right? Okay, so it's a quick one. But it's going to get exciting. We have our panel number 3 on the International Year of Asteroid Awareness and Planetary Defense 2029. So please be quick.
First of all, test. Can you hear us? Kelly and Lars, can you hear me? Yeah, perfect.
Hi, ma'am. Doris, we do hear you.
Oh, great. Thank you very much.
Yes, we can hear you
So
online.
I have a question. During the panel, will we be seeing the audience or the panelists? The rest of the panel. Okay, perfect.
Is that both? Yes, but they're pointing. It's a yes or no question with
there will be both. There will be both.
One way?
There will be both ways.
Okay. Right. I heard it, but I was waiting for the reply from the tech people.
I've answered already. I told him both ways.
At this point, the volume is choppy. The sound is choppy. So.
Okay, please be seated. We're starting very shortly. Can we close that door there? Thank you. All right, welcome back, and thank you for cooperating and keeping your coffee break short. It's my pleasure now to introduce the next panel. It's about the International Year of Asteroid Awareness and Planetary Defense 2029, and I'll hand over to the moderators. Who's doing that? Bill, Romana, Doris? Doris, the floor is yours.
All right, thank you very much. First of all, thank you to the organizing committee and to my colleagues on the panel. I think we would like to I'd like to start by introducing the panelists, and then I have a few slides, literally few slides, and then we can start the questions. First of all, my co-chairs, Ms. Romana Kofler from the United Nations Office of Outer Space Affairs, and Mr. Bill Ayler from, I call him the godfather of Planetary Defense Conference. So, all right, as far as the panelists, I'm going to start with alphabetical order, Dr. Kelly Blumenthal, who is an astronomer and an educator. She is the current director of the IAA Office of Astronomy and Outreach, and she has been very seminal in the work that we had done with the International Astronomical Union. Second is Dr. Lars Christensen from Noir Lab. Lars is an award-winning astronomer and science communicator. He authored many books, dozens of popular science books that had been translated in over 10 languages. He has directed numerous documentary and planetary movies, planetarium movies that have been received with critical acclaim around the world. He's currently responsible for the communication, education, and community engagement for Noir Lab as the head of communications there. But also, Lars is a former IAU director of communications and co-founder of the IAU Commission 55. Dr. Kevin Govender, who is present with you in person. Kevin began work with the Astronomical Union Office of Astronomy Development in 2011 as its first director and has since led the establishment of 11 regional offices around the world. He's, during his previous position as the manager of the Southern African Large Telescopes Collateral Benefits Program at the South African Astronomy Observatory, he worked extensively, especially with the African continent in the area of astronomy for development, including a focused effort to stimulate the local economy of Sutherland through astrotourism. In 2007, he was part of a small IAU delegation that successfully lobbied the United Nations to declare 2009 the International Year of Astronomy. Amy Kaminsky is the lead for engagement branch chief here at NASA, and she has done. She was the program executive for various outreach for the Space Technology Mission Directorate. And finally, last but definitely not least, Dr. Charles Takalana, who is from the African Astronomical Society. He is the head of the Secretariat, and before this, Charles was an astronomy policy researcher at the South African Radio Astronomy Observatory, based in the South African Department of Science and Innovation. Charles is also involved in various outreach projects and is passionate about sharing astronomy with us. Thank you all for joining us. And I don't know if you have my slides there, if possible, if you can share them. All right, thank you very much. I just wanted to give you a quick overview about the effort for the International Year of Asteroid Awareness and Planetary Defense and move on. So on the 13th of April, 2029, the asteroid 999, I think it's not very clear, but anyway, Apophis will be passing safely at a distance of about 32,000 kilometers above Earth's surface. I think you all know that. This will be a critical opportunity. Whoops, it's gone. Okay, my presentation is gone. All right.
No, Doris, we can still see your slides. Your slides are still
up. You can?
Oh, yeah,
okay.
yeah, please proceed. Right. Yes.
All right. So it will be an opportunity for us and a unique occasion for a worldwide campaign to raise awareness regarding the International Year and regarding planetary defense and asteroids, the potential hazards they may pose. We had a proposal that we presented. We started working on it in 2020 that resulted in key recommendation from the 7th IAA Planetary Conference in 2021 and followed by the 8th conference in 2023. This recommendation was presented to the United Nations General Assembly in December of 2024, and in January, the General Assembly of 2025, the General Assembly proclaimed and declared the year 2029 as the International Year for Asteroid Awareness and Planetary Defense. Next slide, please. So this will be a global effort in 2029, and it will help to raise, it will be an opportunity to raise the awareness about planetary defense and the science behind planetary defense. I'm going to just move on so we don't take too much time. Next slide, please. All right, so right now, 4 years ahead of time, we have started by establishing working groups. We have cornerstone projects. We have started exploring partnerships. We are working on developing the effort and creating ideas such as branding, websites, and our impact with social media. Next slide, please. So what are the first steps in this conference right now with our plenary? We will discuss with our panelists the opportunities, the best practices, the lessons learned from various past efforts. And we hope that you would be interested enough to contact us and join the group. You have my email there. And I think the next one is the last slide. And from there, I'm going to move on to our session. But first, I'm going to invite my colleague, Ms. Romana Kofler, to tell us about the IAA PD 2029 resolution. Thank you.
Hello? Yeah, great. Thank you very much, Doris, for this comprehensive presentation. Yes, this was quite a process at the political level, and we couldn't do it with the help of our partners who were engaged in the working group that was led by Doris, but also through our communications channels that Iowa and Same Page have to the committee and its subcommittees. So it was the whole year we put the Iowa and Same Page put a concept note paper before the subcommittee. The subcommittee acknowledged it, put it before and recommended that the committee takes it into consideration. So the main committee, the Committee on the Peaceful Use of Outer Space, in 2024 then endorsed the proposal, the draft resolution, which was tabled by Romania, and that then went to the General Assembly Fourth Committee, which did not vote upon it, but adopted it with consensus. Romania also did a lot of outreach to attract co-sponsoring states. So now we have actually, I think it is a dedicated General Assembly resolution on nearest objects. So if you go to this link here, it's available in 6 official languages, and it also explains not only why this is such a unique opportunity, the close approach of Apophis, but it also talks about nearest objects in general, their definition. So it's a very informative General Assembly resolution on the area that we work on, and I think this is a really unique case also to have a dedicated resolution on nearest objects. And yesterday at the T-4 Apophis session, we could hear from the science perspective, from the perspective of space agencies, what a unique opportunity that is. And not only that, we have at the Space Mission Planning Advisory Group now established a dedicated working group called Apophis Flight Mission Working Group that will actually coordinate and be informed on the planned activities of space agencies for the flyby missions. We also heard how important opportunity this is to for space agencies to actually test their rapid response capabilities. So with that, I would like to pass on to Bill to ask our panelists how we can approach this unique opportunity, how we can raise awareness, how we can gather partnerships and so forth.
Thank you, Romana. And I think everyone in this room should be able to carry the message back to your home countries and so forth and begin the process of getting involved in this international year. It's really a nice opportunity. You are now our experts in the topic. So let me just ask our panelists to start with what, in your opinion, is the value of this international year?
Okay, I'll start.
So the biggest strength of astronomy, and one of the reasons that I got into this field in the first place, was that it gives us the bigger picture. This morning, coming into work, I heard news about the war in Gaza, and over the period of the last few months, we saw incredible changes taking place across the world, incredible challenges that we face on this planet. The occasion of an international year of this, for me, is an opportunity to get people to see the bigger picture. Like the Carl Sagan days when we got the image of, the pale blue dot, and we looked at the perspective of, who we are on this planet and why it's important for us to unite. That spirit, we seem to have lost it if we look at the news in the current media. And I think that the international year like this and the close approach of Apophis gives us the opportunity to really rally humanity, to say that if this object was going to hit this planet, we have to stand together. And in the same way that we need to stand together if an asteroid was going to strike the planet, we need to stand together for climate change, and we need to stand together for poverty and inequality and the challenges that we face today. And so for me, the opportunity is what we can do to make the world a better place by uniting humanity.
Thank you. I think for me, Kevin put it really well. I was actually making my notes while he was speaking, and then he said something that I just saw, rallying the community and the people globally around an idea. The term planetary defense, we're defending our planet against something. Yet, on Earth we've got our own militaries that defend our countries against some threat that they have. But in this idea and this concept, we've got a threat that threatens all of us, and that's something that should be uniting us, and helping us find ways that we can make peace amongst ourselves, so that we can, as humanity, come together in forums like this and speak about how we can. We can protect our planet and secure, humanity, for the future as well. For us, between Kevin and myself, we were, he chaired, I was his vice chair for the IU General Assembly, which was the first IU General Assembly on the African continent. And for us, we used that as an occasion to make the world see astronomy on the African continent differently. And with that, we also used it to bring the African astronomy community together. That here is this meeting, the first time on the African continent. How can we use this to change the perceptions, about our continent, globally? And I think that there is a similar opportunity here, that we can bring the limelight into fields like astronomy and planetary defense, and show people the importance of that field and what people are doing to ensure that we are protected on a daily basis, and know what threats exist to us out there.
I love both of those answers so much. So I'm thinking about three different things that are certainly related to that. One is that this is a chance, of course, to spotlight planetary defense as an issue of global concern. We heard one of the panelists or speakers yesterday reference the Pew studies that have been done over the years, where the public has been asked about, for when it comes to investments in space, what are the things that that are on the top of your list? And planetary defense, along with climate change research, consistently rank on the top. So I think we're talking about a population that is really eager to understand more about what is this issue and what is being done. We also know that there's a lot of misinformation out there to dispel, so we have that opportunity. The second thing is going beyond dissemination of information. I know, I mean, we often think in terms of sharing and outreach, and that's very important, as I just mentioned. But this is also an opportunity, I think, with this year to think about how the public, global publics, can be a part of what we do. So we heard on Monday, we witnessed the exercise, right, scenario, and we found that there were these really vexing questions, and we had a lot of experts here, but like, kind of the thing that was going unsaid was, who's going to make this decision, and how are we going to know what the right decision is? And so I think we have a real opportunity with this international year to engage people around the world and ask them, what do they think? And I'll defer a little bit of detail on this. I think our next question will allow me to share a little more about that. But I'll just say the last thing that I think is important about this year as well is that it's an opportunity for us to build sustainable partnerships and an ongoing commitment by the planetary defense community, by international space agencies, and by government decision makers all over the world, and others to really consider how we prepare for asteroid impacts and mitigation, and to make this a regular part of what we consider as a issue of global concern.
Very good, thanks. Let's see, Kelly Blumenthal, would you like to go next?
Yeah, thank you. So I, of course, agree with everything that my colleagues in person on the panel have talked about. I think astronomy has this really unique way of speaking to the humanity within each of us and really drawing us to science in that way through astronomy, and getting us to think in a much larger way about our place in the universe and our place on this planet. I do think that this international year has a really important role in, as was just stated, talking about misinformation, but particularly in the way that this international year is framed. If we talk about, what if the Earth is going to be hit by a massive asteroid, some people will actually take that as being a literal, the Earth is going to be hit by a massive asteroid, what do we need to do to prepare? And as someone who receives many, many emails daily from people who are concerned about this very thing, this is a really great opportunity to combat misinformation, to show people how to spot it, to show them ways to combat it, and give them ideas and frameworks for understanding scientific information, the scientific process. There's so much rich information that we can impart into the public regarding science in general, but of course, astronomy in particular. And I think also that leads really nicely into this idea of bringing, citizen science projects into part of what we might do for this international year, getting the public involved, getting them to feel a sense of ownership about this international year. I think that's really what will make it successful in the end. So thank you.
Very good, thank you. And Lars Christensen, are you up?
So I actually have some thoughts about international years in general. Would you mind if I spend a couple of minutes on those?
Yeah, please go ahead. Briefly introduce that, and you'll have an opportunity later on, I think, maybe.
Okay, no, then we'll do it later on. I absolutely don't mind that. Let's take it in order.
Yeah, do you have slides now that you want to show?
However order you prefer, yeah. It might be good to do them now because it sets the scene a little more for the topic of the international year. So we've often heard that the IAA back in 2009 was a good project, and I think there is something good to be learned from that experience. The most important topic, I think, is what constitutes an international year, and I think we have many different answers to that, each in our mind. The most important one that I can think of is it's nothing more but a structure coming from an idea. So you can put anything into this, but the idea is to have a centralized component that works with global components, national and local components, and basically herdds the cats in some kind of way. We are in good time with this particular international year compared with IAA. Back then, we only had the ideation in this context would be kind of next year. The setup would be in 2027. The Secretariat plays an important role there. I'll get back to that. We had the peak of preparations in what would be transposed to 2028. Implementation, of course, in 2029, and then a year for closeout. What I find the prerequisite for a good international year is to have good goals and objectives, and I can hear you already well underway with those. Many good things have just been said that I also agree on. But you need a solid structure. You need some sort of a governance structure with a committee at the top. You do need at least one implementing organization. For IAA, we had kind of two and a half, being IAU, the International Astronomical Union, and then the European Southern Observatory, guided by the UN UNESCO office. You need a secretariat. It's very, very important. If there's any message, then that is the one you should hang on to. You need it, and a secretariat that's embedded in a kind of well-functioning or high-powered existing communication unit with all the tools, so you don't have to start from scratch, but can piggyback on that work. You need a couple of people, no matter how you twist and turn, and that also then entails fundraising, something on the order of at least $1 million. A solid website is obvious, but also use it as a repository for all the projects out there, the cats we're trying to herd. And then, of course, a communication strategy. When you set up the project, imagine a project cascade going from global to local. So you need these cornerstone projects, or whatever you prefer to call them. You will soon realize, oh, there are some projects that don't fit in any bucket. You can call them special projects. Maybe some products will be invented, movies, books. You can think of anything that comes along. And of course, most of this doesn't come from the central ideation. It comes from the grassroots out in society, and probably you will have to have some sort of launch event and a closeout event, some sort of centralized global conferences. And in addition to all this, all the grassroots will create projects that you may never actually hear about, and that's the strength of setting up this kind of a structure. Everyone will work for the structure and make that a big global event. There are several levels of implementation. From the Secretariat, you need some partners, some organizations to help you out. The national nodes were exceptionally powerful, and Kelly is today working with many of the same people who actually came out during IAA. So this is a very strong part of setting up an international year. The other things are more or less obvious. In the communication strategy, you will set up a matrix once we realize what to do between the target groups and the products. The spending will start coming in. This is what we did in IAA. We had the fundraising targets as the horizontal lines. We raised about $750,000, and most of the money were spent in the big red bucket down at the bottom, which was salaries for the 2 staff we had, and then the top part here, which was seed funding for the cornerstone projects. But this was a small part of the actual funding. We tried to tally up at the end of the year what was actually spent on IAA, and it was something along the lines of 15+ million out in the environment that we never saw or heard of. So they, by using that idea, could go out and generate funding for the work that they did out in the local environment. And lots of things happened. No need to dwell on that. There is a link on my first slide to the report, which is 1,500 pages with all kinds of nice pictures like these ones here. This was the opening event. My childhood musician, Jean-Michel Jarre, was speaking. That was fantastic. I got to meet him, so that was great. The engine behind was Pedro Russo here. He was the secretary. He was running the show. I was helping a little in the wings, but he was really the instrumental part, and I can only recommend finding someone like that to hire. We had pomp and circumstance as well as stargazing, and projects continued well beyond 2009, and some of them still today. Thank you.
Thank you very much, Lars. Yes, this is amazing. And of course, partnerships will be the key in preparing for the International Year, but also in the implementing the activities. And we at the United Nations Office for Outer Space Affairs will be facilitating the organization in terms of tapping into existing networks, so liaising with member states, liaising with the Committee on the Peaceful Use of Outer Space, liaising with our stakeholders that we work on with daily basis, space agencies, but also reaching out through our networks to the youth. We have, through different projects that we can actually, that are already existing, but can actually be used to spread the word. For example, we have a project, Space for Youth, Space for Women. So we will be using these existing projects and networks that we have, but also we really count on the partnerships, like with the IAA, with the regional and local organizations that could help us spread the word. Obviously, since this is the UN declared International Year, we would be using our global network of the United Nations Information Centers around the world to also pass the message through media advisories and press releases, and those centers then liaise with their local networks, media, who then spread the word in their languages and so forth. So that is a great opportunity. So it brings me to the second question to our panelists on the activities. So what types of activities might the International Year of Asteroid Awareness and Planetary Events include at the national, regional, or global levels? What are your thoughts in that, and what opportunities or trends in engagement might be leveraged?
So for this, I think the big thing to recognize at the outset is there's never a single organization or group that can, say what will be best for every specific sort of community around the world. So I think what's going to be key for this is sort of shared ownership. Like Lars described, there might be activities that we may never see or know about, but if people feel the ownership of this international year, then they would come up with ideas and activities in their local environments that might be completely different from what sort of we as a planetary defense community or so on might be able to think about. So I think the types of activity, I think Lars did a nice description of our experience in the International Year of Astronomy, but I think what was key to that was sort of a combination of a top-down and bottom-up approach. So, from the top-down approach, coming up with cornerstone projects or like big ideas that will help to support communities, but then also allow space for communities, schools, amateur astronomy groups, space enthusiasts to come up with ideas of their own. And I think that's where sort of the magic is going to be, is creating an environment that stimulates innovation at those levels.
Yeah, I agree with Kevin. And I think one other thing is that taking into account that this is something that's happening, at a global scale, it's very difficult to say exactly, what activities would talk to different communities, because different communities, got different needs, got different priorities. So I think one of the first thing, that the Secretariat would have to focus on is on, having a good database, right? A database, where, we can capture, for example, what are these events that people are thinking of? What are the institutions that are, that are involved or they can be involved, and who are the experts, that, people can sort of go to in sort of these different parts of the world, and also making sure that everything is well publicized and having a publicized calendar as well, so people know exactly what is happening, when, and also where it's happening. And I think also seeing how we can collectively develop a well-coordinated volunteer effort, because none of these things, are sort of going to be possible without, having people that are not necessarily paid to do stuff to actually get things done. So how can we, ensure that we sort of do it well? And if possible, like I mentioned, if you're using volunteers, having templates ready for people to do stuff will sort of also be helpful. So if we can have some sort of communication templates, for them, that would also, ensure that, all the events that are organized can sort of be well coordinated and move. Yeah.
And I completely agree with everything my colleagues have said there. I think it will really come down to also being a blend of a couple of different types of activities, one of which is informational. So, thinking about how to develop and share some basic information about asteroid risks and how they're being mitigated. And that's something I think that will definitely be the work of this, the broad planetary defense community to do. And then the other part of it, which I had touched on in my prior remark, was participatory activities. And that takes a couple of different flavors, one of which is really, I think, again, to understand public values associated with asteroid risks and hazards, and bringing those values in to help decision makers decide. I did want to just pull on, just by way of illustration, because that might be a little abstract for some folks who aren't familiar with it, but a little over a decade ago, working with Lindley and others at NASA, we actually did a project called the Asteroid Citizen Forums, where we had two groups in the United States in two different cities, 100 people each, and we brought them together. NASA had never done anything quite like this before, but we brought them together to ask them questions to really elicit how they would feel about her, how they would feel about an asteroid coming our way. Like, who would you trust? What kind of institutions would you trust? What kind of technology would you trust to achieve the mitigation? And this kind of technique has been applied by, I'll say, the Danish Board of Technology is probably the world's leader, where they've done forums within their country as well as around the world, asking people around the world about technological issues, and have even taken those results to the UN. And that's the kind of thing that I think is really, I think we'd be really primed to do, to kind of scale up the thing we did at NASA, to the world and get public values in that sort of way. And lastly, I'll just say also engaging people, again, through citizen science, like the Daily Minor Planet Project, prize competitions, the International Space Apps Challenge, all possible ways to get people and get their ideas flowing in, and not just information flowing the other way.
Thank you. Kelly, what were your thoughts on this, the activities? What kind of events would you envision?
Well, I'm not sure I can really build upon much of what's already been said. I think they pretty much gathered all of my thoughts together. But I will just say, what was just mentioned, having a multi-directional stream of information, not just us telling them, or scientists, people of a perceived position of power, telling people what is correct, and kind of dumping information into people's minds as if they have no other concepts in their heads. That one-directional perspective of information gathering is often damaging for the people who are receiving that information. And having conversations around these topics is really helpful, like those discussion sessions that were just described. I think the one thing that I would mention that we definitely need to think about moving forward is, if we're going to be encouraging a volunteer network, an international network of people who do public engagement work, like the network that is associated with the Office for Astronomy Outreach, the National Outreach Coordinators, then we need to think a little bit critically about what kind of support we're going to give them, whether that's financial support or institutional support, and what kind of projects we expect them to come up with as being like the foundation for a grassroots organization to build up projects, or even come up with cornerstone projects that we might want to do on a larger scale for the international year. And so I think providing funding and prioritizing funding for these projects will be really important, and something that we need to really critically think about as we design this international year, and as we move into how we want to fundraise and how we want to partner with other institutions.
Thank you. And Lars, you have also been very active in producing documentaries. So yesterday we heard already a trailer is in preparation on Apophis, and also, the fact that 2 billion people will be able to see the asteroid with the naked eye, but also in parallel have on their, mobile phones actually the images from the spacecraft during the, close approach, which is actually amazing. From your perspective and with this information, what are your ideas on the activities that could be done also in terms of, multimedia?
So in general, I think the topic couldn't be more pertinent, more relevant, and timely. So that's a big strength of this particular international year. It's a real issue. It's something that concerns so many people, as Kelly said. And I'm pretty sure that once the structure starts getting set up, once there is a website, once there's a little bit of information, people are going to come out of the woodwork with all kinds of ideas. So there is not a great need, I think, to think at much more than the global cornerstone project, and the rest will come basically to you, especially if you can facilitate, if there's a bit of seed funding. Things will work very nicely if you have a good structure.
Thank you. Doris, all yours. The floor with the question.
Thank you very much. Thank you very much, Romana. So what I'm going to do a little bit now, change a little bit the path for in a conversation, and draw from some of our panelists' experience with the International Year, especially the International Year of Astronomy, to talk more about the lessons learned and such. So instead of just having everybody, because I think we're going a bit slow on time, I'm going to ask specific questions. So for examples, with regards to lessons learned, regarding Lars, you mentioned, for example, the Secretariat. And I know that between you and Kevin, there was a strong push to get us funding for the Secretariat. So can you talk a little bit about the role of the Secretariat and how they effectively coordinated the activities across the countries and such? So I'm going to start first with Lars, and then maybe ask Kevin to build on about the lessons learned.
Yeah, it's a very nebulous topic in a sense, because you do need to have a very strong connection with existing infrastructures. You need some big organization. And I won't dare to guess who that might be, but it has to be someone who has the size, sort of medium size, to be efficient, to have all the necessary structures in place. And that's anything practical from procurement to HR, etc. It's a minicosm, if you will, and starting from scratch is just not an option. But not too big that you have too much bureaucracy. And I think that the medium size of ESO back then in 2007, when we set it up, fitted that bill pretty perfectly. So I think that that's an important component, that there is structure, there is a certain size, there is ability and freedom to implement things without having to adhere to too many existing structures.
Kevin?
Hello? Yes. I think Lars said it all, and also in the presentation. Maybe just to say, get a nice person as a secretariat. It makes all the difference to have someone with a good personality who can, because they're going to have to deal with people of all cultures and backgrounds and so on. And if you have someone who's like too much of an introvert that can't engage people, they won't be able to lead a community. So the person, the character of the person is important as well.
Thank you. Thank you very much. I want to talk a little bit, Kelly. You mentioned about the national organization, the national representative of outreach. Can you tell us more about the role they play? What are the guidelines you generally provide them from country to country?
Sure. You mean within the context of the International Year or within the context of the OYO?
With the context, yes.
Yeah, of course. So I wasn't directly involved with the International Year of Astronomy myself, although the Office for Astronomy Outreach and the National Outreach Coordinators are both legacy projects of the International Year of Astronomy in 2009. So for the National Outreach Coordinators, which were previously the specific points of contact, or the SPOCs, for the International Year, they are a network of more than 120 countries. They each have teams of people that they work with to do the work that they need to do within their communities. They have networks not only of people that they engage, but also other science communicators within their region that they kind of amplify the work or snowball the work out that we're trying to do on an international scale, they do on a local scale, and then push that out farther. And I think one of the things that makes the NOCS network, the National Outreach Coordinators Network, so successful is their ability and freedom really to localize and make relevant all of the work that we're doing at the OAO. That's not just about making things culturally relevant. It could be something as simple as just doing a translation. But making sure that all of the materials that are coming from the OAO and from the IAU and the other offices are made available to open access for those communities, made available to, are brought into those communities explicitly, and are also made relevant for their community. So I think in the terms of an international year, if you're talking about building up grassroots projects or getting global recognition, getting people excited on a global scale, these national outreach coordinators would really be like your seed within each of these communities that can then amplify the word out. And they'll serve a really important function, I think, for this international year as well. And I do think, if we're talking about understanding how an international year might succeed, aside from doing like strict evaluation and understanding very clearly what your goals and your objectives are and what kind of data you want to collect, I think having a successful international year implies that the work that you're doing now will live on beyond that 1 year. So everything that the OAO does, all of the work that the NOCS do now, lives beyond 2009 and has been going strong for nearly 2 decades. And hopefully that's something that we can continue doing with the international year that we're organizing now. So I hope that answers your question. If I didn't cover anything, please let me know.
Very much so, very much so. And actually on that sound, I would like to remind everybody, Alex Carl had put a poll, so please take a moment and answer the poll. We would love to hear from you and have your opinions about this. I think I have one more question here to talk about, and maybe then if quickly you can maybe I'll start with Charles and then move on. With your opinion, Charles, how will partnerships and networks be important for the success of IYAPD?
Yeah, I think partnerships and networks are very important. Especially if you want your information to reach all the right people, and you want to cast your net as wide as possible. And for example, I'll just take my experience with the African Astronomical Society, sort of ensuring that we've got country contact points, that we can send the information to, And we could also use those contact points as point of input as well, because we might want to go a certain direction, but that does not necessarily cater to the needs of the community. So allowing those to sort of be two-directional, streams of communication is also very useful. And also, I think people are always willing to get involved and do something. And I think the sort of assumption we sort of always make, sort of be reluctant that maybe people are not, are not going to necessarily be willing to do something. For us with our experience with IU General Assembly, we just put out a call to people saying, if you come to the IU General Assembly, maybe you can pass somewhere and engage in outreach activities. We thought we'd get tens of people, and we got almost, over, I think about 600 people saying that they're willing to take part in outreach activities. So we should always just ensure that we communicate that all that information in a way that works, and I think that probably move in the right direction. Yeah.
All right. Well, I'm going to give a chance to each panelist to answer this question. So, Kevin.
So in terms of partnerships, I think Charles has said it all. Maybe just to say that again, I'll come back to this point about partnerships. If you can connect with the human beings behind organizations, it makes a massive difference, because it takes making those relationships, building relationships with individuals. So beyond just looking at organizations, building those people partnerships so that people can bring in those networks. I don't think we use Hollywood superstars enough in our outreach efforts, and sort of the influences of the world. They should be part of this team. Yeah.
Thank you, Kevin. Amy?
Oh, I could speak to that, but I know we're also running short on time, so I want to just make sure we're able to, if you had any other questions as well. I don't know if you were planning to go on.
No, please go ahead, and then we can maybe 5 minutes before we close open the questions from the audiences, yeah? Would that be okay with you, Doris?
That would be fine. Thank you very much.
Yeah, I mean, I think that the partnerships are going to be really key to disseminating information, of course. And I mean, we've heard a theme of this meeting has been about, again, trusted relationships and being able to get the word out into communities. And that's something I know that we've done quite a bit of. I think about to the work we've done within NASA, we do rely on partners to get content out to about science out to our communities in the United States. We have a solar system ambassadors program where we train people to actually go out and talk to their communities, and I could very much see things like that being a model for use here. We also use networks. I think they can be valuable in other ways. We have also a NASA Night Sky Network where we have astronomers who go out to communities with their telescopes, and I see that as a potential model for sharing the wonders of the night sky, including Apophis for those who will be able to view it. Perhaps networks can be relied upon to make that connection with people.
Thank you so much. And just before we open the floor to Q&A, a brief intervention from all the panelists. We've heard from Kelly that the success factor would be for the year to go beyond 2029, so its effects. What, in your view, maybe Amy, what is the success factor for the international year from your side?
Yeah, I mean, I think that's a huge one. The sustainability factor is huge. I also think just getting asteroids and planetary defense into discourse, into the vernacular. If we're hearing those terms more and more in college and community college science and engineering courses, if we're hearing them more in local, state, and national governments in terms of disaster management planning, I mean, I think those are markers of success. And I'll just say also, I think, asteroid movies are here to stay. And I think if we start seeing things like responses along the lines of what I1 and Same Page work toward, and those start to become part of those movies, then I think we'll know we have delivered the message.
Great, Charles.
Yeah, I'm just going to be very short about it. I think instead of looking this as an opportunity for or rather to raise awareness. Let's look at it as an opportunity to create not just, the next 4 years leading up to the international year, but rather creating a decade of transformation, within the space of planetary defense. And maybe then, you're going to build a more planetary defense conscious, global society by building those kind of activities. Yeah.
So maybe I'll use the opportunity as a South African and the freedom we enjoy in speaking freely to call out the elephant in the room and say that one of the successes will be if we never have to face a situation where one of the biggest governments in the world is talking about cutting science funding. I think that if we can use the International Year from now to say to all governments that if we did not invest in science, if we did not invest in NASA, then we would not know about Apophis and we'd not know about something else that's coming. And I think that level of security is something we need. So, when we talk about trust in science, trust in people, do not underestimate the power of the name NASA and the brand NASA. People trust NASA. If you're talking about, 50% cuts in NASA, it's going to be bad for the world. So if we can use this international year to change that, I think it would be a significant success.
Yeah, Lars, very briefly, and if we can have the Q&A already on the screen, so.
Yeah, I loved what Kevin just said. So even if you don't care about boring rocks in space, you will care about the future of the Earth, right? So that's a phenomenal statement right there. I would say the goal should be to raise 1 million, activate or touch 1 billion, and have 100 national nodes. Then this would be a resounding success.
Thank you so much. Shall
I'll just say that we have had Chinese representatives here for past conferences, and so I think they will certainly help in their area. And let me just inject one other thing. This conference series started 20 years ago, and one of the speakers at that conference basically says that one thing we have to overcome is something called a giggle factor. People just didn't believe at that time that asteroids were going to ever hit the planet, and they just sort of laugh it off. But I think we've done a lot of work since that time to basically improve that. And so I just congratulate all of you for doing what you're doing and moving this concept forward.
Yeah, and this question is actually interesting. What will people actually see with the naked eye when Apophis flies by? Yeah, so over expectations, right? It will be a dot and like a star. And I know we are very excited about it, and this community is particularly excited about it. But yes, managing expectations is also an important part of this. But I think imagination is a driver and of curiosity, and I think we should also, with this close approach, tap into our imagination and creativity. And before also to add on the comment by, on the engagement from our Chinese counterparts, of course, CNSA is a member of Space Mission Planet Advisory Group. They cooperate with IAA. So they're, a spacefaring nation that is a member of the Committee on the Peaceful Use of Outer Space. So we do engage with them. We engage with, all spacefaring or emerging spacefaring nations, developing countries. So I think that's our strength. We need to use as a convener, as the Office for Outer Space Affairs, and reach out to all. Yeah.
I think, do we have time for the Q&A with the audience?
Yeah. Oh, would you like a mic? Please take the,
Even with a $2,000 telescope, I think you can do pretty good for Apophis, and many people have one in their backyard. So, just a consideration.
Yeah, definitely. Get a telescope through Amazon, maybe. But Doris, would you like to do some closing remarks, because we're running out of time? We're so sorry. We will mark your questions, and yeah, we will take them into account when we prepare for the year. Doris, the floor is yours.
Thank you very much, Romana. First of all, I want to thank our panelists for taking time to be part of this conversation. And obviously, the conversation is still starting now. I invite you all to join us. Please send me an email, doris.dow@nasa.gov. We are in the process of putting together listservs so we can send you all updates and hopefully plan our first working group meeting to start planning our international effort. Definitely want to also thank the local organizing committee and my colleagues Romana and Bill for this wonderful session. Thank you very much.
Thank you very much. Thank you all.
Thank you again for this fascinating panel. Looking forward to 2029 and the years before to get ready for that. Before I let you go to lunch, so we reconvene at 1:35. And I just want to shout out three people who, in particular three people, but many of you have been engaging with the content in the app for engaging more with the content, what's happening here on stage. And especially with the poster session yesterday, we had 3 random poster challenges. And the first 3 people to reply to each of one, we have a little goodie bag for you. So I want to welcome Dora Föhring, Rosie Wilson, and Francesco Giannotto. Congratulations. We have a bag down. You can grab one. They're all the same, so you can just pick. And with that, thank you for engaging. We have more prizes for those of you who want to engage deeper. We also have some virtual prizes coming up, so don't be afraid if you're at home and can't be here. We're thinking of you as well. And with that, I'll leave you for lunch, and we'll see you again at 1:35.
Is somebody coming here first, or we take over? Is there any announcement before we start? Oh no, I'm opening. So after you. The title of the 2-5 minutes.
Please be seated. Can we close the doors so we can get started? Thank you very much. I welcome you back after this great lunch. Just one quick reminder, after the session at 4 o'clock, we'll meet outside for a group picture. So if you want to be on that, please be there. And without further ado, I'm handing over to the session chairs of the NEO characterization panel, Max and Marina.
Thank you very much. So welcome to the NEO characterization session. So we will start first. The first talk was withdrawn by Michael, so instead we will have two shorter talks from people that have a poster here. And so the first talk will be from Rosie Wilson about asteroid polarimetry. So Rosie.
Thank you, Maxime. Hi, everyone. My name is Rosie Wilson. I'm a graduate trainee at the European Space Agency, and I'll be presenting the work I did for my master's thesis. So polarimetry is a technique that's often used for calculating an asteroid's albedo, but one of its underexplored applications is actually for the classification of asteroids, so as an alternative or as a complement to spectral classification. So we know that when sunlight is reflected from an asteroid towards the Earth, it becomes partially linearly polarized. We know quite well that this relationship, what it is like for asteroids, and how it changes with phase angle. So it's been well characterized. It's negative at the lowest phase angles, and then this is below around 18 to 20 degrees, and thereafter it increases with phase angle and becomes positive. So the specific parameters of this curve are quite individual to an asteroid. For example, the magnitude of the minimum, and the intercept and the gradient. However, some previous studies have collated and averaged the phase polarization curves of various asteroids of different spectral types. And by comparing the polarimetric data of a single asteroid to these averaged curves, we can actually get an idea of what the spectral type might be. So we used the Liverpool telescope, which is located in La Palma. It's the largest currently operating robotic telescope in the world, and its polarimeter called MOPTOP. We used this to observe 6 different NEOs and focus primarily on the Didymos-Dimorphos binary system. And this actually is observed by the LT as a point source, so it's not resolved. And our data from Didymos is shown here on this plot in blue. So we can see it actually aligns very well with the blue curve on the graph, and this is actually the average curve of an S-type asteroid. So from this we can classify Didymos as an S-type, which agrees quite well with other classifications made in the literature. We were also able to calculate its albedo, so this is done from the gradient of an empirical fit to Didymos's data at the inversion angle, which is where it crosses 0. And we calculated this to be 0.203 with an uncertainty of around 6%, which also seemed to be in good agreement with what's been found with other methods. So some similar observations of Didymos were actually made by another team using the VLT, and they observed immediately before and after the DART impact, and this data is in red on the plot. So the polarization signature of the DART impact is quite evident in the swap from the red circles to the red crosses. You see a sudden, quite dramatic drop in polarization, and we attribute this to the reflected sunlight from not the asteroid surface, but the diffuse dust particles in the ejector tail from the impact. For the Liverpool telescope, our signal-to-noise ratio was much too low to actually confirm this secondhand. Additionally, we only started observing around 5 weeks following the impact, and by this point the tail was just about visible. However, its polarimetric signature had dated, so our overall trend wasn't able to confirm this. But still, I think not bad for a 2-meter telescope. So the data set of potentially hazardous asteroid polarimetry at high phase angles is currently quite sparse, but the Liverpool telescope is actually ideally placed to expand it. So as you can see from this graph, the polarization behavior of asteroids diverges significantly at high phase angles. So this is beyond around 40 degrees. So even sometimes just a single data point above this can be sufficient to classify an asteroid. The overall morphology of a phase polarization curve is actually above this point, not usually linear. It will actually decrease into a maximum, usually typically maybe 70, 60 degrees. But our current models don't have enough data points at this range to incorporate it into our models. So in all, we got some really interesting data of Didymos and also observed some other NEOs to repeat this analysis. So please do come and see my poster next door if you're interested. I'd be very happy to discuss it more. And thank you very much.
Thank you very much, Rosie. So just a reminder, we will do the Q&A session at the end, just before the coffee break. We will have a 10-minute Q&A session, and please use the app to write your question, or we can take question in the attendance. So now we have a 5-minute talk by Shinju Oriuchi about radar in the Southern Hemisphere.
Hello everyone, I'm talking about radar observations from Southern Hemisphere. We are using one of the deep space facilities in Canberra. We started this radar observation almost 10 years ago, and our deep space complex is operated by CSIRO, and at the same time CSIRO operates radio telescopes in Australia. So we transmit signal to asteroids, then we receive signal from other radio telescopes in Australia. And recently, we expanded these collaborations using other optical telescopes within Australia. We named this acronym Southern Hemisphere Asteroid Research Consortium. But this conference is a great opportunity to extend collaboration to other Southern Hemisphere continent. Okay, so this is an example of our radar observations. Last year, 2024 MK was discovered, and we soon organized radar observations from Southern Hemisphere. Our observation was first radar observations prior to Goldstone. We started with CW observations, and we found large offset from the frequency we expected for the echo spectrum. And we used that offset to refine the orbit. And that in the middle of observations, we used a better orbit information. Then that coordinate is applied also for the subsequent Goldstone observations. And we piggyback Goldstone observations for delayed Doppler images like this. And so Goldstone transmitted with their 70-meter dish, and we received this with another 70-meter dish in Canberra. And this is one of the most sensitive bistatic radar next to the Goldstone Green Bank bistatic. Yeah. And also, we had an opportunity to use optical telescope. This image is taken from University of New South Wales paper telescope. And we did astrometry and also light curve measurement. And this is another project based at the University of New South Wales in Canberra. We set up an anechoic chamber facility to simulate model asteroid. And this is an example for the contact binary asteroid. And the idea is, we observed asteroid 2024 ON last year, which showed very similar pattern for this waterfall plot time versus frequency. Yeah. Our ultimate goal for this kind of experiment is to simulate profile for polarizations depending on the surface compositions and the surface roughness. So yeah, we just started this project, and this is ongoing. And lastly, I want to talk about Apophis 2029 encounter. So Apophis will be approaching from declinations minus 30 degrees. So the Canberra radar will be in better position than Goldstone when it's approaching. We can observe up to over 10 hours before the nearest encounter. And as you see this picture, the Apophis will be flying above Australia and go to Indian Ocean, then Africa. So we are speaking to colleagues in South Africa, such as Scarrow Meet, which will be operational by 2028, and they have a capability to receive our uplink frequency. Finally, I want to leave with a title of 3 posters from our collaborations. First poster is for overview of our project, and second is an atomic chamber experiment, and third one is extended collaboration with optical telescope. Thanks.
Thank you very much, Shinji. Now we will have a talk about JWST as a tool for early characterization of potentially impactor by Andy Rifkin.
Hello, everybody. It's a pleasure to be here in South Africa and at the Planetary Defense Conference. I will point out that when I wrote this abstract, it was really looking at previous PDC exercises and tabletop exercises and how JWST might do if it were used in those sorts of situations. In the interim, 2024 YR4 showed up, and so a lot of this talk is about that, and a lot of the people who have done great work on 2024 YR4 were not on the abstract, but I want to call out Thomas Muller, Eric McLennan, and let's see, Brian is probably already on that. Brian Holler is already on there, so thanks to them, even though they're not on the abstract. Next slide, or do I do that myself? I probably do that myself, don't I? All right, so just to quickly go through here, what are JWST's capabilities? JWST is probably the most capable astronomical facility we have. I'm going to say probably because there are some other great things out there like ALMA, for instance. It's a 6.5 meter telescope at Earth-Sun L2. It has several instruments that cover the range of visible and near-infrared and mid-infrared wavelengths. It is extremely sensitive, and it can get wavelengths that are difficult or impossible to get from the surface of the Earth. It has limitations, of course. The most important probably is the field of regard. It can only observe objects between solar elongations of 65 degrees and 135 degrees. So it gets a lot closer to the sun than one can easily get to with ground-based telescopes. We were hearing about the Twilight Survey for Rubin earlier. This gets closer to the sun, but it cannot observe at opposition or anywhere close to opposition. There are large overheads because of its nature and the nature of what they're trying to do with it. The time necessary for observations can really pile up. So maybe you only want 2 hours worth of observations, but to JWST, 2 hours of observations can be 5 hours. You can't point 2 instruments at the same thing at the same time. Everything is pointed at different parts of the focal plane. So if you want to use more than one instrument, you need to move the telescope slightly, and you literally cannot look at them across with multiple instruments at the same time. There are things like data rates that have to be considered in some cases. There's the meteoroid avoidance zone, so they prefer not to look in one particular direction if they can help it. And then to really maybe one of my pet peeves, or my bets noir, there's a very large oversubscription rate. It's very hard to get time unless you can really convince them you need to get time. But something like, hey, there's an Earth impactor coming is a thing that they think maybe is worth doing. So again, it's exceedingly capable. It's a sensitive facility. Here on the right is a plot from a paper of Christina Thomas's from 2016, which looked at using JWST to look at NEOs. On the x-axis is wavelength, on the y-axis is basically time, well, it's a brightness, and then the upper horizontal-ish lines, broken lines, are to saturation. The lower set are to get a signal to noise of 10, I think, at different wavelengths and different filters. And basically, the takeaway here is those things down on the lower curves are 5-meter objects that are observed like tenths of AU away from the Earth or more, and you still get these great signal-to-noises with them. You can schedule JWST with no overhead penalty if you have an observation you want to make 2 weeks in the future, and it can greatly reduce size uncertainties. These wavelengths in the mid-IR are the ones that we use to get to measure sizes. Those are the whole idea of a mid-infrared search telescope is because you want to use those wavelengths because they're much better in a lot of ways for getting asteroid sizes. So I figured we should be using these, we should be taking advantage of this, and what better way than to look at some of the exercise targets that we've had in the past at these meetings and other similar exercises. So I modeled the JWST observability of the exercise targets using the actual launch rate of JWST in December 2021. Horizons very helpfully has the the ephemerides, the simulated ephemerides of the exercise targets, so you can very easily go in and say on such and such a date what was the solar elongation, etc. So 7 scenarios involved impacts after JWST was launched, and in all of those cases, the exercise target was observable by JWST before impact. There were several exercises that involved impacts that occurred before JWST was launched. Obviously, JWST would not have been able to observe those. But if JWST had been launched, in 2010 or 2003 or something, if you assume JWST had been in operation, those would have been observable. I just assumed a very small amount of time, a nominal amount of time, 20-minute integrations per filter, 3 or 4 filters, representative thermal properties, and the SNR was very high in basically all cases. This upper left plot shows solar distance versus, I can't quite read that even though I should know what it is, flux in, I think, the 12.8 micron filter. The curves show the estimated minimum and maximum flux for 2 different thermal properties with distance. The horizontal lines show basically representative signal to noises that you can get in representative times. And the dots there are all the exercise targets. The hardest one is 2019 PDC. Some of you may remember 2019 PDC as when we saved Denver at the expense of New York City. And that one was difficult because it was fragmented, and the fragmentation happened when it was far from the sun. So in that case, we only ended up getting something like signal noise of 3. I'm really blowing through my time here. So the bottom line here is that these were the toughest cases, and even in those toughest cases, we were able to get information several months before the impact date, even in the ones where the one where it was going to hit North Carolina 6 months after discovery, we were able to get information at least a few months ahead of time. Jumping ahead now to YR4, we all know this, we can skip this. Here were the basically minimum and maximum size put on top of where we are now before JWST. And this was an important target because it met a bunch of the benchmarks for recommending space-based reconnaissance. The only one that was iffy was whether it was bigger than 50 meters or smaller than 50 meters. And that made it a great target for JWST because we could determine that. So we proposed for director's discretionary time. As the impact probability reached 1%, we were able to take advantage of measurements by Peter Pravets and Julia De Leon and Nick Moskovitz that gave the spin period and the likely composition. We were able to fold that in to influence our experimental design, observational design. We proposed most of the observing to happen in March, and we received 4 hours of observing time, which was 10 hours of JWST time. And it entered the observing window on March 8th. We maybe heard a lot of this before, but to go into a little more details, we got near-cam images on the 8th of March, which gave us some astrometry. The light curve is being extracted and worked on. On the 26th of March, we were able to get MIRI observations, which we were not able to get earlier due to guide star acquisition issues. And the results there, the signal to noise we got was limited by calibration uncertainties. It was not the brightness of the object. So again, it was very sensitive. We were able to do great with that. We found YR4 to be 60 plus or minus 7 meters diameter, and more to the point of that, slide a few slides ago, we determined that it had, we thought, about a 92% chance of being bigger than 50 meters. So if there were still an appreciable or an impact probability greater than 1%, Detlef would be telling the same page that they gotta get on the ball here. It turns out the thermal properties were very unusual. They were not what we were expecting. Maybe because it was a rapid spinner, but it was much colder than we were expecting, and consistent with a lack of a sandy regolith or a dusty regolith. We put in a memo to IWAN about 30 hours after the data was received on the ground. The impact probability was down by then, but we were trying to rapidly turn it around as a bit of practice, and then we submitted a research note to the WS about 24 hours later. Astrometry got submitted, and the team is working on peer-reviewed papers, and that took the size uncertainty down to about like this. So our next steps with YR4, the last hours of our cycle 3 DDT time are coming up shortly, I think Sunday night, Monday morning. My understanding is we expect the likelihood of a lunar impact to remain a few % even after these next observations. It could even go up a little bit. YR4 is a faint target in early 2026. It's about V of 30. But, as I said, JWST is extremely sensitive, and so it's possible to get from JWST. It would be a difficult observation, but we're still considering it, and those observations might establish whether it would hit the moon or not. Ideally, and I'm going to get gonged for this, I'm not going to get gonged. Oh, I just get a time's up. Where's the gong? Ideally, there would be some program that JWST or Space Telescope or NASA, I guess, would set up that would formally establish that if there are triggers, if the same kinds of triggers perhaps that trigger an IWAN memo or some other set of triggers would trigger Space Telescope to use, to make observations, have some time set aside to make observations. So we're working on a paper on describing how best to use JWST for these purposes. Positional measurements were just a nice to have for us, so we didn't try to optimize on those. It could be a key JWST capability, and we're thinking again about how to do that. So conclusions, there I am with JWST in the back, I'm in the front. In scenario cases, in the real life case of YR4, JWST observations can quickly provide good size measurements or constraints for objects we're interested in. We're still determining the best ways to design astrometric observations for NEOs, but I think the YR4 experience gave us a lot of good information on that. Thank you. And we were able, it was really good for us that we had complementary ground-based light curve and spectroscopic measurements. Those really helped us say, okay, it's a 20-minute rotation period, we're going to have 20-minute exposures. Things might have been harder to interpret if we didn't have that information. And then a nominal amount of JWST time can do a tremendous amount of good. So I will leave it at that. Thank you for your time.
Thank you very much, Andy. And now we will move to Marco Micheli on follow-up activities and developments from ESA Planetary Defense Office.
Okay, thank you, Maxime. Thank you, everyone. And this talk will be slightly different from the other ones in the session because I'm an astrometrist mostly. So not exactly characterization, but it's not either discovery, so it's going to be somewhere and ended up here. So this is the perspective of what we are doing at ESA, at the NEO Coordination Center, Planetary Defense Office. This is just a summary of how we operate. It's a simple graphic that outlines that there are basically 3 pillars of how we deal with the threat from asteroids. And we as observers are clearly here in this very simple box called detect. But what comes out of this, for our purposes, at least for the dynamical assessment of an object, is the product, the out product is astrometry. And astrometry is the basis for the next step, that is the assessment of the threat that an object poses. Astrometry here is kind of general, but it's basically 2 types, as we know. The most obvious one is what we've seen this morning. It's survey. So it's the discovery of new objects in the sky. ESA has just started dealing with that a little bit. You've seen a presentation this morning by Rainer Kresken about the test we do with some small telescopes we have. And this is a test for the actual real survey telescopes that we're building, and they're soon going to be operational, the FlyEyes. And I invite you to look at Dora's poster to know more about this, about the survey part. What I want to focus the rest of the talk is the second type of astrometry, that is the follow-up. And that's what we've been doing for basically more than a decade by now, by growing a network of telescopes all over the world with the goal of reacting to various astrometric and observational needs. It's actually not a trivial thing. This is just a map of the network that we have. You see there are telescopes literally in every continent, more or less. And why is that important? Well, I have a simple infographic here that I like to show is, well, most telescopes now that do survey, until ESA's FlyEye comes into play, are kind of in the US Southwest, Hawaii. And we are Europeans, so we are here, and if we want to do follow-up with European facilities, we would need to wait the Earth to rotate for 12 hours. 12 hours is often not enough, and I'll show you why. So we have to find places where there are telescopes we can use that are not in Europe, not in the US, somewhere else. And that's the goal of why we have a network and why we try to do this. It's really important, actually, and it's something that people tend to not consider, that rapid response for what we do is not trivial. And rapid can be hours. This is just some plots that I took out of JPL Scout like a year ago or something. It's an Atlas discovery, nothing particularly interesting on the object itself, except the first image, the one to the left, is the uncertainty that the object had 1 hour after Atlas discovered it. And if you look at the axis, I don't know if you can see it, it's a few, in that case, just a few arc minutes. So easily recoverable by basically anybody. 6 hours later, and the uncertainty is now many degrees. 24 hours later, so if you had to wait one night and do self-follow-up from the Discovery Station, you end up with basically the whole sky. So this is true also for normal asteroids. Anything that is close enough to us will have an uncertainty that explodes unless it's follow-up on timescales that are less than the rotation of the Earth, and that means that we need to have longitudinal coverage. Imminent impactors, of course, are even more critical. Sometimes they don't even exist anymore, 24 hours later. And another thing that is not trivial is that for the immediate follow-up, parallax matters. So having a lot of telescopes in the same place is not as good as having one telescope far away and observing at the same time from a completely different direction. And we've seen that with a few imminent impactors in the past. A single observation taken from another continent basically nailed the orbit uncertainty almost immediately. So, of course, imminent impactors are rare. We don't only use our telescopes to do imminent impactors. We use them to do regular follow-up. This is just a little bit of our cut on how we do things. Of course, the main source is now become, as most observers do, NeoFixers, Catalina's fantastic prioritization tool. I want to point out, though, that since we are the Planetary Defense Office, we care about planetary defense threats. So we supplement the Catalina NeoFixer list with direct targeted observations of every object that ends up in our risk list. So any object that is a possible impactor and has a non-zero probability of impact. And this is something we specifically target. It's our mandate. It's what we want to do with our telescopes. It's our main goal. We've been doing follow-up with some of the facilities we have. You may have seen that the 84 has become one of the leading follow-up facilities, despite being a tiny telescope, 80 centimeter only, but it's doing very well. Another thing we care about is not just doing astrometry, but it's doing good astrometry. And good astrometry doesn't just mean not messing up the numbers and doing them right, but it's to doing them in a formally correct way. And formally means a few things, not just measuring array and deck, but also giving uncertainties to everything we measure. So giving uncertainties, believable uncertainties to rate ascension and declination, studying the time uncertainties and time biases, and checking the coordinates of our telescopes. Sometimes we discovered that some coordinates that the MPC had were off by hundreds of meters, and that's not good if you want to observe something very close. And all a bunch of little subtleties that make astrometry at high precision levels not as trivial as it might seem. The good thing is that this is actually really useful now, because in the past, well, we were sending single liners to the MPC in this MPC 80 format. A lot of this fancy information was not even reported, didn't even get out. Now we can. Well, we have ADES, that is a format designed to properly record all of this information. So every time you do astrometry right and you compute all these quantities can propagate through the orbit determination centers and can actually be truly used. Another thing we like to do is to do challenging observations, challenging in various ways. Of course, there's the obligatory wire 4 picture there. The first challenge is going faint. We have a long-standing agreement with VLT to use an 8-meter class telescope to go faint, and that is, to my knowledge, the latest ground-based detection of wire 4, 26.5 from VLT. Little dot there, you can see it's pretty well detected. We can routinely go to 27 with 8-meter class telescopes. Going fast, observing objects that are actually really fast. Imminent impactors are the obvious ones, but not only. And then going low is something we care. We've seen the yellow elongation observations discussed earlier today, but we do like to do that. We have a telescope that Rainer has presented this morning on the Andes. We can point at the horizon, basically, and what you see there is not a really bad image with really horrible vignetting, is when you point into the mountains in the Andes, and you, of course, see mountains. Another thing we like to do is to try and push the limit of what we can do with our telescopes. We've heard multiple times about synthetic tracking, so I'm not going to spend time on that. What I want to spend a few seconds is the following thing there, the going faint with small apertures. This is something we've been experimenting quite a bit in the last couple of years. We have this 18-centimeter telescope in Calar Alto in Spain. Pretty nice telescope, but pretty average. It's a Schmidt, an old Schmidt refurbished. And we said, well, can we really push an 80-centimeter telescope to go really, really faint? And the answer is yes. What you see there is a magnitude 24 asteroid observed with an 80-centimeter telescope. And well, if you're asking how is that possible, the answer is very simple. You spend a whole night on it. But it can be done. And I really want to point this out because in the epoch of LSST coming around and probably being flooded by a lot of high-priority faint asteroids, this could be the way to get the follow-up. There's a lot of smallish telescopes out there that they can, in theory, invest a long amount of time, large amount of time, into chasing one particular importer object. So let's keep that in mind, everybody who has a meter-class telescope. Don't forget, you can do that. You can go down to 24th, and it's actually really cool. The last to the right is something we've been doing a bit. It's observing artificial objects, not per se, not because we care about artificial objects per se, but because they are sometimes a very nice test case for observing something really fast, really challenging, and for which, in many cases, we have a ground truth, so we know exactly what we're looking at. And to conclude, I just want to point out the importance in general of archives of images. We've seen some discussions of that earlier on today, too. Every images we take with any of our own telescopes and our collaborating telescopes is made available on our website within, say, a few days to maybe a week of being taken. The archive has grown quite a bit, and to connect to something that was asked earlier, how do you search for it? Well, everything we have in our archive has been indexed by this fantastic tool that I strongly recommend from CADC, from the Canadian Astronomy Data Center. It's called SSOIS, and it indexes basically almost all the large aperture telescopes on the planet. You can search by asteroid, or you can search by observations, by ephemeris. It's a search tool designed to search moving objects. So if you search there, you put the name of the asteroid, you put the orbital elements, whatever you want, you get all the fields that have covered that particular area of the sky, including all of ours, all the images that we've taken with our project. And that's more or less all I have. I'm just going to leave the summary here of what are the highlights of how we do astrometry and observations. Little note there, I'm taking the last 30 seconds I have to point out the last sentence there. We're always happy to expand our network. So if anybody has telescopes in poorly covered areas, so areas of the world where you've seen in my map, there's not that many facilities, we are very happy to try and set up a collaboration. So if you do, please contact us. These are our email addresses, and we'll be very happy to set up a collaboration, informally, scientifically, any way you want, to help the planetary defense observing world. Thank you very much.
Thank you very much, Marco. And so the next talk will be by Marina Brozovic on status of near-Earth asteroid radar observations at Goldstone.
Hello, everybody. So I'm giving this talk on behalf of Lance Benner, who couldn't be here. Okay, so we'll be talking now. We heard about South Hemisphere radar. This is our North Hemisphere radar. Goldstone is currently the most powerful radar on the planet after the demise of Arecibo in December of 2020. So we are looking into 70-meter diameter dish. It is fully steerable, covers 80% of the sky, everything north of -35. It has a powerful transmitter. Most of the time, most of our targets are about several hundred meters in diameter, and we are observing within 1/10 of AU. There were many recent improvements at Goldstone since just 2020. So for example, we have much better design of klystrons. These are vacuum tube amplifiers, which are the core of our transmitters. They've been redesigned. They're very stable. We have no equipment problems. We had many, many smooth runs on them. We're getting a lot of time at Goldstone, so it's not unusual that at least 2 weeks of the month we are observing for at least 5-6 hours every day. We can react much quicker. We used to need aerospace clearance because of the nearby military space, not anymore. We have a lot of new software that is continuously checking the latest impacts and cross-checking with our current schedule and putting just automatically targets of opportunity, and that is really thanks to work of Shantan Naidu. We also recently got this monostatic switch very fast. Our mode of operation is basically we use a single antenna. We transmit from it and we receive from it, and you need this switching cycle between. And at this point, it's so fast, it's far less than 1 second, that we can observe monostatically within 1 lunar distance. So all this is very good news for us. So here I'm showing you, this is a history of radar observations from 1980 onwards. So what you're seeing in blue, this was our SIBO observations, and you see it was a real powerhouse. In 2019, it detected 120 near-Earth asteroids, and then you see in the red, this is the Goldstone rising, and you can see that every single year we're starting to break the record from the previous year. So, for example, last year we observed 55 objects, and probably this year we're going to observe even more. But overall, we had 5-fold increase in Goldstone detections over the past 15 years. I'll be showing you a lot of numbers, but I'm really going to just really concentrate on the ones that are important. Many times we get asked, well, how much can you really observe? If you had unlimited resource and unlimited time, how much can you really observe? So just let's say in 2024, in theory, 500 NEAs were detectable. By detectable, I mean that you just ping the asteroid and just get that bump in the echo power spectrum. That's the minimum detection. Many of them, you get really ranges, you get images, and you get much more data. So regarding potentially hazardous asteroids that we all care about, so in year 2024, there were 32 PHAs larger than 140 meters that were detectable, and we observed 31 of them. So we are already observing everything we can regarding PHAs. So regarding anything greater than 20 meters, 20 meters is kind of our nominal guideline because the PDC office basically said, anything, if it's smaller than 20 meters, there is a trade-off with a science value that you can get out of it. And so, unless they come really close. So regarding greater than 20 meters, there were 170 potential targets. We observed 30% of those. So pretty high number. And then everybody else. So everybody else, that means, few meter rock flying around. And overall, we observed 11% of what could be observed. So here is, since start of the radar observations in 1968, with the detection of asteroid Icarus, we have more than 1,100 objects in our database. We have 138 main belts, and we have 23 comets. So most of our population that we observe with radar, these are potentially hazardous. Again, we observed overall 20% of currently known potential hazardous asteroids that are known to date, and that is making up more than 40% of our radar sample. It just happens to be, if something is large enough, it comes close enough, the odds are sooner or later we can ping it with radar. So it comes pretty naturally. We also have, we're really starting to study how the near-Earth asteroid population looks like. So radar is very effective with detecting binary systems. We currently know about 100 binaries in the near-Earth population, and radar discovered 60% and observed 80% of those. We actually, there are 5 known triple systems in Earth population. They were all discovered by radar, 1 by Arecibo and 4 by Goldstone. And also we are pretty much, radar is the only way that you detect contact binaries, because I showed you yesterday during my talk that in the light curves you really can't tell apart whether something is elongated or something is a contact binary. So currently we have definitely 60 and probably another 20 candidate contact binaries, and they were all discovered by radar. We can argue whether Itokawa was actually discovered by Hayabusa. So recent highlights that I'm going to show you. So some planetary defense stuff and some really neat radar imaging pictures. Here is I'm going to skip Apophis. We did contribute to the success of DART mission. So after DART ended up impacting Dimorphos, there was a cloud of debris. But for radar, so optical observers were not able to observe, but for radar wavelengths, we could penetrate through the debris. We were observing only 12 hours after the impact, and just the back of the envelope calculation that Shantanu did showed that the orbital period did shrink by 36 minutes plus minus 15. So this was the early indication that this mission was a success. And of course, we ended up with time getting much more radar and imaging data, and optical light curves did an incredible job, and so all together came to make DART such a success as it was. Shinji actually showed up this object. This is just how we saw it. So Goldstone was both transmitting and receiving, as opposed to with the Southern Hemisphere radar, we were transmitting and they were receiving. So you see, this is whenever we see these kind of smaller objects, something in the order of 130 meters, they start looking pretty interesting because they are angular. They very rarely do you see a perfect little sphere, although sometimes it does happen that as well. We have 3.75 meter imaging capability, which puts quite few pixels on something that is 130 meters in size. Again, these are radar images. These are not optical images. I can't go in too much detail. You just have to, just kind of, you definitely can figure out that this one is definitely an angular-looking object. Here is a binary that we observed recently. There is a close-up on the right-hand side of the primary object. There is a lot of detail, all these bright specks on the surface. We truly are imaging surface boulders because this is, again, 3.75 meter resolution, and this is a relatively large object. We estimate about 400 meter diameter. So that means that, if you're looking this half circle that you're seeing, that is something we call visible extent. And if you just count number of pixels, multiply by 3.75, you would come up with a proxy for radius. So it's very quick assessment of the size of asteroid. What is unusual in this is this really widely spaced satellites all the way in the back. The binaries usually are 4 to 5 primary radii. Their satellites are not separated more than that, but in rare instances they are, and this was one such instance. Unusual look at the binary system. This is kind of top-down view, and you get a really kind of good look at kind of flattened pole region and then sloped hemispheres. So you have that kind of, this presumably looks like Bennu or Yugu, that kind of object. And this is a contact binary 2024 ON. This is smaller than Apophis. The long axis is only about 350 meters, but with 3.75 meter resolution imaging, you can see a lot of detail, and this is about 6 hour covering its almost full rotation, and again, bright speck is probably a surface boulder. So a lot of detail that we can see, and we have many times a year we have opportunity to image something like this. There are no shortage of really great targets coming up. So what I'm showing you here, this is date of close approach until 2032, with finishing with YR4, distance in lunar distances, size roughly. And what is going to be our signal to noise per day. So as the FA22 is target of opportunity, it's not anymore. Torino scale 1, it's been downgraded, but things are happening really fast. And then you can see, Apophis is coming in 2029, extraordinary target, but there are many, many others. Finally, in 2032, we'll be also observing WIRE4, because we cannot detect it in 2028, is still too far for us. But no shortage of radar work to come. So thank you very much.
Thank you very much, Marina. So our next talk will be online by Tobekile Sandra Ngwane about the rapid response fully automated NEA follow-up program with SAAO 1 meter Lesedi telescope. Do we have our speaker online? Okay, I mean, we cannot hear you if you are trying to speak or mute it, I don't know, or maybe the connection is not good. Are you talking? No, we cannot hear. Can you type in the chat? We cannot hear you right now. Okay. So in the meantime, let me remind you to use the app if you have a question, and ask your question in the Ask the Experts Session 5 Annual Campaign Radar and Rapid Response Observation. So it's not called Q&A, but it's in the top of the list of talks. We still cannot hear you. Yeah, but there is no other talks. We can start to do the Q&A in the meantime. Yeah. So for Marco, if you can come here. So what was the equivalent exposure time for the 0.8 meter telescope to reach a 24th magnitude?
A pretty easy one, about 5 hours.
Is there a question in the audience? Can all the speaker maybe come in? We will do the Q&A session and do the talk after the Q&A session if we can fix the sound issue. So for Marina, you mentioned that many 140 meter size asteroids are quite angular in shape. What kind of errors or performance degradation are you likely to suffer if you insist on treating them as spheres?
Okay, so I'm not completely sure what is error of performance degradation. So I'm just going to guess that this is about estimating their sizes. So the only way to do that correctly is if you do some shape modeling work. We obviously have a software that can invert radar data into three-dimensional shapes. And then at that point, from the vertex shape model, you can determine the equivalent diameter sphere. So that is going to give you very accurate diameter. So I'm guessing this is about the size of the asteroids.
Okay, thank you. So another question for you. Orbik is a secondary of 2005 LW3.
Yes, so the primary, as I said, is quite large. It must be a dark object because it was like a factor of 2 larger than we expected. So the primary was about 400 meters in diameter, and then we are estimating, in range, if you count the number of pixels, that the secondary is perhaps in the realm of 150 meters. So just because it's narrow doesn't mean it's small. That's a Doppler. You have to understand in a delay Doppler images on a horizontal axis, this is a Doppler frequency. So this is just telling you how fast parts of the object are moving toward you or away from you. And then on a vertical axis is a range. It's your distance from the radar, and that's the true physical dimension. So the difference in size in a horizontal dimension between primary and secondary just means that the primary is spinning very fast, about 3.7 hours, I believe, and then the primary is spinning very slowly in the realm of, more than 10 hours.
Okay, so another question for Andy. Do other telescopes have better TOO systems for NEOs that JWST should implement?
For JWST, part of the issue is that they have to do the scheduling involving a whole lot of things that obviously a ground-based telescope, like if you go to Keck or you go to IRTF or something, it's just you just need to kick the current observer off if you've decided that's what you're going to do. The scheduling problem for JWST, and I think for other space telescopes that don't do surveys, is really involves a whole lot of things, and also involves sending data down, involves messing with their reaction wheels sometimes, and a lot of stuff. So I think something JWST specific, the team who do operations up there are really great. They're really accommodating, and they've put a whole lot of person hours into the problem of scheduling over the years. So I think they've probably got it about as good as they can.
Okay, so for Marina again, do you know how well inside the Hill sphere of influence is the secondary of the binary asteroid you showed?
So no, we did not do that calculation, but yes, that is a very good question. There was something strange with the orbit of that secondary, because we observed the system only in 3 days. And when we just tried, quick orbit fit, it just was not working. So it did have a very close Earth flyby. So unfortunately, it's one of those kind of, we would need more data to claim something really interesting. But as of now, we just have something kind of, this tantalizing hint, but we cannot really claim anything definite.
I have a question for Rosie. How much time can you spend to observe NEOs with the podimeter at the 2-meter telescope?
In terms of the other things it's used to observe?
Yeah, how much NEO can you observe? Like, how long can you spend on the telescope?
In terms of hours, I think per night we were maybe getting 2 hours of data. Okay. But generally the LT is just used for observing things like gamma ray bursts with polarimetry. So I think they would have a lot of time for more observations of NEOs.
Okay, it could be very interesting to get more observations.
I agree.
So I've got a question for Shinji. If you thought about putting in meteorites in the chamber your team is using to get realistic data, radar signatures for calibrations? And if so, how large, what shapes, and what type of materials would you test?
Yeah, we've been thinking about this. This is very interesting experiment, and meteorite is a good candidate for an anechoic chamber experiment. And in Canberra, we have a Geoscience Australia. They have a collection of different meteorites and minerals. So I think we should collaborate with those people. Yeah.
Okay. So I think it's for Andy. Why do you think YR4 thermal observations were so unusual? Just spin, bare rock, and would that be unusual?
Yeah, before I forget, a couple people I should have called out at the start were the folks who did the astrometry, including Marco and Max and Luca. So for the thermal models, basically the thermal skin depth is dependent on the spin rate of an object for 20-minute spin period. The skin depth, which is how far the heat can penetrate before coming back out, is only a few centimeters. So it could be bare rock, but it could also be if you're covered in 10-centimeter gravel. I don't know if it's still gravel at 10 centimeters. That would look like bare rock thermally. And there are folks in the room like Thomas Muller and others who could confirm or deny. But it needn't be like literally bare rock. It could just be, larger than 5-6 centimeter rock.
Okay. And the last question for Marco. Why do you think time uncertainty is that important?
Good question. It's important because, especially for fast-moving objects, it pretty quickly becomes the dominant source of your uncertainty. If you have something that moves many, many pixels during your exposure time, of course, if the time you exposed is not known, it becomes basically a moot point to have an accurate measurement of the coordinates themselves. What I want to point out, and it's I think the most important thing, is that people think that having a good timing means having a well-synchronized clock. And I want to point out that's not the end of the story. You also need to make sure that your system does not introduce biases. Those are the most dangerous things. Because if it's just noise in the clock, it's going to average out probably. But if it's a systematic, if between when your clock reads the signal and when your shutter exposes, there is a finite non-zero amount of time, then all of your observations will be biased in time. And that's where the real danger happens, where all your observations are biased and you torque the orbit away from the reality.
Okay, thank you very much, everybody, for the question and the answers. And now we will get the last talk of the session, and we will do a very quick Q&A for this talk by Tobekile, Sandra, and Guane on rapid response with the 1-meter Lesedi telescope.
Okay, cool.
Okay, we can hear
hello.
you now. We can hear you.
Okay, great. Sorry about that. Okay. So hello, everyone. My name is Tobegile. I just completed my master's degree at the University of Cape Town, and I'm also a student at the South African Astronomical Observatory, working with Dr. Nick Erasmus and Professor Paul Groot on a project that focuses on the rapid response and characterization of near-Earth asteroids. Cool. So far, we've discovered 38,000 near-Earth asteroids. And if you look at the animation below that shows the discovery statistics from 1995 to 2024, you can see that the median size, it shows the number of asteroids versus the age magnitude, and we can see that the median size over the years has been shrinking. And if we jump to 2024, we see that the median size for that year was 36 meters, and 61% of the objects for that year had diameters less than 50 meters. So small NEAs can still cause significant damage, as shown by the 18-meter Chelyabinsk meteorite, which damaged a lot of buildings and injured people. So we need to continue observations of these objects because the follow-up characterization still lags behind. And rapid follow-up is more important because these small NEAs quickly fade in brightness as they move away from Earth. So this project aims to enhance the rapid follow-up observation capabilities for newly discovered NEAs using the Lesedi telescope, and that's what I'll talk about today. So for our observations, we use the Lesedi telescope, which is a fully automated and robotic 1-meter telescope. And on that, it has the Mkodi instruments, which we use to collect images in G, R, and I, as well as unfiltered images. So we have an automated Python script which checks NASA's JPL Scout web page every 15 minutes for new discoveries. And if it finds objects that are observable for that night, it will automatically generate an observing request and send that to the observatory control system. So we've got a 10-minute cycle that goes through the G, R, and I filters interspaced with clear images. So all of this happens in robotic mode, and there's dedicated software that will retrieve the latest schedule and execute these observations. So there's systems also in place to notify the PI, which is me, once the observation is done. So all of this happens without any human intervention. So here you can just see 3 examples of some asteroids that I've observed. And these are unfiltered images. And from that, we manually measure the astrometry. And this means me manually selecting the asteroids as I blink the images. And I submit this to the Minor Planet Center, which contributes to the orbit refinement of these NEAs. So for images that we collected in the G, R, and I filters, we run that through a photometry pipeline. And this can only be done once the asteroid has been designated. So the GIF below just shows the photometry for about 73 asteroids that I've managed to get color out of. And that is your G, R, and I filters in green, red, and orange respectively. So with that, we use it to compute the photometric colors. And that's how we get the color indices, the G minus R and R minus I. Cool. So just to summarize some of the observations we've done 230, we've had 230 successful observations, a majority of which have been done within a day of discovery. So if you look at the first plot that shows the number of asteroids versus the asteroid size, you can see that more than about 3/4 of our observations had a diameter of less than 100 meters, which was our first goal to probe the small NEA population. And if you look at the second plot that shows the number of asteroids and this versus the time difference, which is the time difference between the discoverer's last observation and our first follow-up observation. And you can see that more than 60% were done in less than a day, with 10% being done in less than 3 hours, which was our second goal, rapid response. So a faster response time would be possible, but we're limited by the reporting of these discoveries to the Minor Planet Center. So if you look below, I show an excerpt from the Minor Planet Center for asteroid 2023 QN7. And this date here is the last observation by the discoverer, which is Atlas in Sutherland. And the second date here is our first follow-up observation. And the time difference between that is 57 minutes, which was our fastest time. And this is because the Atlas node and the Sadie are both located in Sutherland SAO. Cool. So going back to the final calculated G minus R and R minus I colors, we use that to try and determine the likely taxonomic types of these asteroids. So we do that by plotting them on a decision boundary that was trained by a machine learning algorithm in previous work done on this project. And what this boundary does is it separates the asteroids into their taxonomic types based on where they fall in this boundary. And for this project, we considered S, C, X, D, Q, and V type asteroids. So this uses the Bus-de-Meyer classification taxonomic scheme. And this plot here just shows 73 of the asteroids that we managed to get color out of, including their uncertainties. So for example, if we look at this asteroid here, 2024 EJ1, you can see that its error bars do sort of likely go into other regions. And now when we want to determine the most likely taxonomic type, we don't just consider its point, but we consider the uncertainty bars too. So what we do is we generate 10,000 random pseudocolors around the point and around within the uncertainty, and we and then we classify these pseudocolors individually, and then we tally up those numbers, and a percentage for each likely taxonomic type is returned. So if a target has a taxonomic probability of more than 50% in a specific class, it's assigned that classification. So if we look at that previous asteroid, it had 64% in the X region, and we classified that as possibly an X type. And for asteroids that don't meet that threshold, for example, 2024 EP3, it had its highest in the X region with 28.9, but it did not meet that threshold that we set, so we just left it as unclassified. So the plot on the right just shows the asteroid type distribution versus the asteroid taxonomic types. And for this, we didn't just consider the individual classifications, but we considered all the tallies that made up each taxonomic type. And you can see that we had more of the S and C types and significant number of X-type asteroids too. So just to summarize this, we've observed 230 NEAs, and 15 of them were considered potentially hazardous asteroids. And we found that about 75% of our asteroids had a diameter of less than 100 meters, and 60% of them were observed within 1 day of discovery. So our results sort of match previous work done on this, in the sense that we did, if we consider the S, V, Q as the stony types and the C and X as the non-stony type, we did find a almost 1:1 ratio, which is what was found in other work done on this. And then also found that we had a slightly smaller number of S-type asteroids, and we also had a significant number of X-type asteroids. And we think one possibility of this is because we observed a different size population, which had a lot of fainter near-Earth asteroids. So that could have caused that difference. So for future work in this project, the aim is to automate the astrometric measurements and expand this to larger telescopes to study fainter discoveries. And this will be what I'll be doing for my PhD at Stellenbosch University. So yeah, thank you. I wish I could have been there in person.
Thank you very much. So we have time for a quick question. Do you observe other targets beside those receiving scout alerts?
Could you please repeat that?
Do you observe other targets beside those receiving scout alerts?
No, for now we're just observing targets that are on scout.
Okay, and quickly the last question. How did you generate the Monte Carlo samples?
How did we?
How do you generate the Monte Carlo samples?
The Monte Carlo samples. I can answer that question just right after this. I'm not sure how to answer that properly right now.
Okay, no worries. So let's thank again all the speakers for this session. We are running a little bit late and we need to reconvene here at 3. So the coffee break will be only 15 minutes because we have the photo after this talk, and you can come. We have the photo after this session, and we need to take the bus to go to Cape Town. So let's reconvene at 3.
Okay, hello everybody. I think we are ready to start. This is the last session. So the idea here, so each speaker gets 10-minute slot and they can use some of the time for questions. So please keep submitting your questions, but it's not clear that we may actually not be able to get to it. So let's get the session started. So the very first talk is the characterization of high priority NEOs from the 4.3 Lowell Discovery Telescope by Nick Moskowitz.
All right, good afternoon, everyone. How do I advance? Well, we'll figure the top button? All right, cool. All right, my name is Nick Moskowitz. I'm from Lowell Observatory in Flagstaff, Arizona. I'm going to talk about some of the NEO work that we do with the LDT, the Lowell Discovery Telescope. So this is sort of a brief outline of the talk. I'll touch briefly on the diverse instrument suite that we maintain at the LDT, and then I'll give some sort of recent highlights on sort of 3 classes of objects that we regularly study at the LDT. That would include virtual impactors. We've heard a lot about YR4 the past 3 days, but I'll focus instead on a recent object, FA22, which was sort of the next Torino 1 object that was discovered just a few weeks back. I'll talk about imminent impactors, in particular 2022 WJ1, and then very low delta V objects, and in this case I'll talk about 2024 PT5. The LDT has a pretty diverse instrument suite. So at the back end of the telescope is an instrument cube. It's literally a cube, and 5 sides of that cube are occupied with different instruments, and so we have access to 5 instruments on any given night, and we can switch between instruments in about 60 to 90 seconds. So it's a very diverse suite of instruments and also very flexible. The current instrument suite includes both imaging and spectroscopic capabilities. Our imager is a moderate field of view, 15 arc-minute field of view, monolithic CCD called LMI. It's great for light curves and colors down to about 23rd magnitude and astrometry down to about 26th magnitude. We have spectroscopic capabilities, both at visible and near-infrared wavelengths, typically able to go down to about 19th magnitude to do taxonomic and compositional work. We are excited about some of the future instrument capabilities. In particular, we have an instrument that is shown there in its crate that literally arrived yesterday, I think. That's an instrument called REMOS that was built at NASA Goddard. This is a near-infrared camera and spectrograph that will push our sensitivity at those near-infrared wavelengths by a magnitude or 2. So we'll be able to start doing additional characterization down to about 21st magnitude in V-band. And then we're additionally working on a new visible wavelength spectrograph to arrive in a couple years to do taxonomy down to about 21st magnitude. I'll just note at the bottom there that we are currently seeking partners on the LDT, so if any of these instruments are interesting to you, there are other instruments as well, come talk to me. I'd be happy to discuss further the opportunities for access to the LDT. All right, let's get into the sort of different classes of objects that I want to cover here today. The first of those is sort of a case example here of a virtual impactor, 2025 FA22. This is kind of the next object after 2024 YR4 that at least raised a few eyebrows. Marina noted earlier, this is no longer a Torino scale 1 object, but at least when I put this slide together, it was. We received an alert for this object based on the Torino scale and collected observations shortly after that. We spent about 2 hours on target. We were able to get light curve photometry there on the left that shows just sort of a steady increase in brightness over about 2 hours. So that's suggestive of a pretty long rotation period for an object this size, maybe a rotation period of something like 8 or 10 hours, which may be helpful to know for planning of radar observations. And then the colors, the broadband colors we collected on this object suggested it's a fairly ordinary Q-type or S-complex-like asteroid. So very common amongst objects in this population. The Q-type taxonomy suggests a diameter of something like 120 meters. So this is sort of a rapid response to a virtual impactor that has a favorable future apparition. We're also interested in imminent impactors, and so here's a recent paper. I'm going to show 2 papers. The first of these is focused on the Earth Impactor 2022 WJ1. Both of these papers are led by Lowell postdoc Teddy Coretta. And so WJ1 was an impactor that was detected shortly before impact. And here it is to scale, roughly, next to the, LDT. So not necessarily a planetary defense hazard. But it is an important case study because the capabilities needed to follow up objects like this are very similar, independent of what size object you're talking about. So the need for rapid response, the challenging observations, the ability to collect data efficiently and quickly is important regardless of the size scale we're talking about. In this case, WJ1 turned out to be one of the smallest asteroids studied and characterized to date, something like 40 centimeters across. So here we see WJ1 streaking through the LMI field of view. We followed this object all the way until it passed into the Earth's shadow. So we have the last reported astrometry of this object before it disappeared from our images, and we were actually quite confused for a while about why we weren't seeing it anymore, and then realized, oh yeah, the Earth has a shadow. So these are 10-second exposures. You can see how trailed the object is. That makes measurement of the photometry challenging. We're able to measure each of those trails to look for light curve variability within the trails. We did that in multiple filters as well to extract the colors of the objects. The brightness variations along the trail suggest that this was a rapidly rotating body. The colors suggest a silicate-rich surface like ordinary chondrite meteorites, which suggests a taxonomic type and an albedo that implies something like a 40 to 50 centimeter body. One of the things I don't have time to talk about for this imminent impactor is that we did a lot of telescopic characterization here, but there was a whole set of complementary analysis done in this paper looking at the video fireball observations of the bolide coming in through the atmosphere. And through those independent analyses, the study of the asteroid in space and the bolide coming in through the atmosphere through video observations, we derived orbital and compositional information, and those were highly consistent with one another, which was a really nice confirmation that the tools we use and the techniques we employ are if we believe them both, are consistent and hopefully accurate in terms of the information we extract from those data sets. And that was the first time that this had really been done in an intentional and comprehensive way to see how the fireball data and the asteroidal observations compare. So the last object I want to talk about here is a low delta V asteroid, 2024 PT5. The title of the paper maybe gives away what we think the conclusion of this is. It's on the lunar origin of near-Earth asteroid 2024 PT5. We quickly responded to this object due to its low delta V. It's sort of the lowest 0.1% of all NEOs. Whenever we find objects on orbits like this, there's the question of whether it has a main belt asteroid origin, whether it's a piece of the moon, lunar ejecta, or whether it's an artificial body. And so when we collected the spectra here from the LDT, as well as target of opportunity observations at NASA's IRTF, we see a clear indication of a 1 micron band, a 1 micron absorption band, which is just something that doesn't show up in artificial rocket bodies. So it's a clear case of this object being natural. When we did a coarse compositional analysis on this object, we actually find that spectroscopically this looks not much like what we see amongst typical asteroid spectra, and instead is more closely matched by spectroscopic measurements of lunar samples. And so our conclusion is that, in fact, PT5 is most compositionally consistent with material from the lunar highlands. So that makes PT5 the second confirmed NEO from the moon. We estimate that there could be dozens, maybe as many as 100 NEOs in our current sample that are pieces of the moon that are sort of masquerading as NEOs. And it's unclear, I think, at this stage, how lunar ejecta influence both impact rates and NEO population models. We have a source here that's not terribly well treated or even understood from an observational perspective in regards to these properties. So I think that's very much an area for future work. So just to wrap up here with a little bit of time left, LDT is a flexible instrument suite, good for rapid response to some of these challenging targets. We're focusing a lot of our efforts on virtual impactors, things that may impact years or decades from now, imminent impactors, and very low delta V objects. And so with that, I'll stop, and I think I have about a minute for questions if there are any in the audience.
Do we have any questions online or in the audience? I can quickly give you the microphone. Well, I don't see anything. So, okay, well, thank you. The next speaker. So our next speaker is Measuring the Menace, Advances in Determining in the Sizes of Hazardous Near-Earth Objects. It's my co-chair, Max Devogé.
Thank you very much, Marina. So, yeah, today I will talk to you about the summary of a workshop that we organized in Germany in November 2024. And the goal of that workshop was to gather the community working on near-Earth objects to try to improve our ways to determine the size for NEOs. So to put the workshop in context, so we have a task entrusted by the European Union to ESA within the space program to promote networking between member states and research centers. So the goal is to organize every year a workshop with a topic related to planetary defense. So in the previous years, in 2022, there was a workshop on NEO imminent impactor warning coordinations. And in 23, we had the workshop for increase of emergency response agencies' awareness on the NEO threat. So as I told you, this year, in 2024, we organized a workshop on size determination of potentially hazardous NEOs. It was between the 11th and 13th of November 2024 at ESA in Darmstadt, Germany. So there was 101 registrations with 40 of these participating in person in Darmstadt. So all the presentations have been recorded and are available on the website of the workshop. You can get the QR code there to get to the website, and the QR code will be in all the slides, so you have time to flash it. So the objective of the workshop was to invite the scientific community to get a state-of-the-art discussion on size determination of NEOs, and to discuss with observers and modelers, so to bring like the different communities to improve the strategy for reporting photometric observations, because to get better size determinations, we need precise photometric measurements. And foster new collaborations between the different communities, and at the end of the workshop, generate a list of actions and recommendations that the community can take to try to improve the size determinations of asteroids and NEOs in general. So first, I need to explain a little bit how size is determined for like many people here that are not experts in size determinations or observations of NEOs. There is the main way to determine the size is the relationship that you can see here that is linking the diameter, the H magnitude, absolute magnitude, and the albedo. So the albedo is simply how bright the object is. Is it white? Is it black? It's a range between 0 and 100%. So, and the H magnitude is the absolute magnitude, which is a definition of how bright the object will be observed on the sky if it were located at one astronomical unit from both the Sun and the Earth, and at 0 degrees of phase angle, which is the angle between the Sun, the asteroid, and the Earth. That geometry is impossible unless you are located on the Sun, but it's just a definition. So correcting from the distance is pretty easy, but correcting from the phase angle is not that trivial, and it was a big part of the discussions we had. So one of the questions, without entering into the details, but what model should we use to model this phase curve variations, these phase angle variations? So there was a discussion, should we switch to maybe HG12 star, which is a better model than HG that has been used for years. And so if, since both of them are like one parameter, so G is one parameter, we could fix a G12 star at a certain number, like we do with the G of 0.15, but trying to do some modeling after the workshop, we see that using G12 star with a fixed parameter or the G at 0.15 doesn't change much. It reduced the bias from 0.15 to 0.10, but it's still a slight improvement on the bias when we get the true H magnitude and the H magnitude when we fix this parameter. So the other results is that there is a need for a central database of photometric observations a la MPC for astrometric observations. So the Minor Planet Center is getting a lot of observations, but it's mainly for orbit computations. So you can report the photometric measurements, but it's not the main goal, and sometimes these have very high uncertainties. So a proposal was submitted to the IAU to set a working group to explore the need for an IAU-approved global archive for small body photometric data, and to complement the one that we have at the MPC. The proposal was approved by Division F, and it will report their funding before the next IAU General Assembly. So now the best method to actually determine the size of an object is actually using thermal observations. We already heard about thermal observations, and the reason it's much better, but it's much harder to get, it's because the thermal observations is basically independent on the albedo. And so the flux that you will receive will depend on the size. And since you know the temperature, because you observe in the thermal infrared, you can get estimation of the size. So it's summarized very quickly, but that's why thermal infrared is really important. So the request from the community was that ephemeridis services should provide the phase angle with its sign. So it means, is the asteroid trailing or leading the sun? It's really important for thermal observations to get that information, and it can help the thermal modelers to get easier modeling of this object. So as a response, the ESA and EOCC is considering adding the sign as an option in its ephemeridis services, so it will be able to retrieve that sign easily. To finish with other ways to get the size is polarimetric observations. So polarimetric observations are very useful because they actually give you the albedo, but it gives you the albedo independently on the size, actually. It gives you the albedo independently of the H magnitude. So even the rotation of the asteroid doesn't matter for polarimetry. So when you observe an object at a given phase angle, you will get a certain degree of linear polarization. And that degree of linear polarization is inversely proportional to the albedo of the scattering surface. So if we have calibrations of what is the degree of polarization that we should observe for such and such albedo at such and such phase angle, with one single polarimetric observations, we can get the albedo of the object. And through the H magnitude that we observe through photometric observations, we can get the size of the objects. And combining thermal infrared polarimetry and optical observations, we have a much better comprehensive knowledge of what the asteroid is, its taxonomy, its composition, its size, etc. So the request was the calibrations between polarimetry and albedo should be published, and we are currently working on publishing that paper. We have a lot of polarimetric observations that still need to be published, and we have that calibration, and it just needs to be published. So to finalize, there were a few talks about stellar occultations. It's a very niche technique. It's very powerful, but it's hard to implement. Only a few objects have been observed in stellar occultations. Basically, when an asteroid is passing in front of a star, that asteroid will disappear for a few seconds, and if you time how long it takes for the star to disappear and reappear, you can get information of the size of the objects. But you need many, many observers to get the shape, to get the size, and it's still very hard to implement for near-Earth object. It has only been done for couples of NEOs. So to finish the result of the workshop, the committee should switch to a more recent phase curve model, as the old AG system is displaying H magnitude biases. It will be extremely beneficial if surveys could target specific NEOs when they reach at minimum phase angle. So the surveys could try to target the opposition on the sky to get these very low phase angle, because they are really important to get the H. fMRDs can get the sign for the phase angle. There is a need of a database for photometric observations, and also a database of thermal infrared flux. Getting all the missions and ground-based telescope observations will be useful, and calibration between polarimetry and albedo. So thank you very much for your time.
Perfect timing and all the time you had. So the next talk is online. So that we have Eric McLennan online. Can you hear us? Excellent.
Can you see me?
We can see you and we can hear you. So Eric will be talking physical characterization of potentially hazardous asteroid Icarus.
Should I share my screen?
Yes, you can share your screen.
Thanks.
Yeah, you can run everything. Yeah, let me know. So are you going to advance, or do you want me to advance the slides?
Can I advance?
Yes.
Is this okay?
Sure.
Okay. So you can see my normal.
We see it excellent. Yeah, this looks good.
Okay. Yeah, thank you for having me. I'm Eric McLennan from the University of Helsinki, where I'm presenting from today. So I hope my internet connection is stable enough that you can hear me. I'll be talking about the potentially hazardous asteroid 1566 Icarus. Yeah, this was discovered back in the 1960s, but we still don't know very much about it. It was actually the first asteroid to be observed by radar, and has a very low radar albedo. We know something about its size down here, around 1.4 kilometers in size. Coming back up to the middle here, an interesting work has identified Icarus as possibly linked to a meteor shower, the Taurid Perseid meteors. And so this could be some kind of lead to some kind of debris hazard if Icarus were to disrupt. And there's been some work on rotational disruption, near-sun disruption, and maybe tidal disruption that could be relevant for Icarus. So in this talk, I'll do sort of first a attempt at the physical characterization from existing observations. I say pre-existing. We did some ground-based observations last year, so I'll present on those after the initial shape modeling and thermophysical analysis on existing observations. And I'll wrap up by talking about planetary defense prospects. So I have to move quickly here. Basically what we did was take all the available light curve data of Icarus, most of it from the light curve database, and some new Gaia DR3 data points, and ran an inversion code on all the light curves to generate a large set of shapes and different spin axis orientations, as you can see here, the pole latitude, longitude, and an example of the shape model that we got. We confirmed the previous rotation period, which is very fast at around 2.26 hours. We then took existing NEOWISE and Spitzer data of the thermal emission of Icarus, and with a thermophysical model and all of these different shapes and spin poles that you see, tried to fit the infrared data set using all of these shapes. And the result from this was we got a diameter size. Max just talked about how good or useful thermal infrared data are at constraining the sizes. And so this is another piece of evidence of that. We constrained Icarus's thermal inertia to be quite low, very close to the moon, with some moderate surface roughness. And going back to the spin pole constraints that we got from the light curve inversion, we were able to actually narrow down the uncertainty or shrink the uncertainty of the spin pole to a very smaller, much smaller region, as you can see by the red points here, which are low chi-squared fits to the thermal data. Icarus was targeted by radar in 2017, I believe, or the burst from 2017, where they were able to constrain the Yarkovsky or semi-major axis drift rate of the orbit. And we took that and ran it through a Yarkovsky model to constrain the bulk density and bulk porosity using S-type composition. And so you can see the histogram of the result of that. We took this bulk porosity and bulk density and computed surface slopes using the nominal shape model. And as you can see, we plot the local gravitational or local surface slope, so what the net force with the gravitational and centrifugal forces are. So 70 degrees, sort of very high. You would feel some kind of push towards the equator at these latitudes here. So this sort of hints at a more susceptible areas more susceptible to landslides. All right, so this wraps up the sort of analysis of pre-existing observations. And I realized sometime last year, that in June, Icarus would make a close approach to Earth. So this was a good opportunity to perform ground-based infrared observations using a new instrument on the IRTF. Before I talk about that, I'll just briefly say how useful or sort of the background for infrared observations, motivation of observing in the infrared. So the asteroid surface absorbs sunlight and based off the albedo and is re-emitted. Thermal inertia can affect this temperature distribution across the surface, which is dependent on some of the heat transfer, the thermal conductivity. And based off where the asteroids are in the solar system, how much sunlight they absorb and re-emit, the black body temperature peaks at around, let's say, 10 microns. And this black body curve will shift up or down. It's directly proportional to the size. So this is why it's so useful to observe asteroids in the infrared. So the observations last year that I mentioned, we observed, where we use the infrared telescope facility, IRTF, on Mauna Kea, which has this MERCI instrument, mid-infrared instrument, that can currently observe in several bands. We chose the N band, which is at 10 microns. The RTF also has this small finder scope they call OPHE, which is actually useful for simultaneous visible photometry. And I'll talk about some of the observations we took with OPHE as well. So observing from the ground in the infrared is very difficult because of Earth's atmosphere. It's very warm and it doesn't allow infrared light to transmit at all wavelengths. But fortunately, there's a transmission window around 10 microns, as you can see here in this top plot. And the N-band filter, which is given in the blue curve here, is centered at 10 microns. So right in that transmission window where we can observe from the ground. As I just mentioned, the Earth's atmosphere is very warm, so we have to take images in a very unique way and to reduce the sky emission. And the way this is done is by taking hundreds of very short exposures and stacking them, and then moving the telescope to another position. So we nod the telescope between two positions, A and B, and subtracting the stacked images from these, we can actually reveal the source that we were trying to observe. So sources are not visible in individual images, but only after the subtraction and stacking can we reveal the source. So here's an example for Vega. There's a paper on RTF MERCI operation and reduction, which I recommend if anyone's interested, go give that a read. And I'd like to especially thank Andy Lopez-Aquendo for helping out with these observations and planning. Maybe I'll spend not too much time on this slide. This is just about how important it is to calibrate. Just like with any photometric system, you need to calibrate infrared photometry by observing many stars. Maybe a bit more important is how you stack the frames can affect how much flux you get. And of course, the flux being proportional to the size can affect what size you actually end up with. So Icarus was actually too faint to be seen in the AB pairs that were stacked, and we had to optimize the shifting and stacking procedure that was recommended by Hora et al. And as you can see here, if we just take initial offsets that were provided by the telescope control system, it's not enough to properly align Icarus in the images. So we had to perform lots of pixel shifts to properly reveal the source. I'll go a bit quicker here. So the fluxes that we got from RTF were consistent with the size and thermal inertia that were constrained from the space-based results. So this validates the MERCI and RTF as a legitimate way to get thermal fluxes. There was one night that might have been kind of worse than the other two.
Eric, you need to wrap up. You're out of time here.
I'll just skip to this slide here. So yeah, we detected Icarus with RTF MERCI, so it's capable of observing kilometer scale asteroids. I believe we could have observed 2024 YR4 with RTF, but only in a small window. And of course, without radar, we're kind of reliant on infrared observations. So I'll skip ahead too. Thanks for your attention.
Thank you very much. So the next speaker is Mikael Granvik, and he'll be telling us how tidal disruptions increase the number of asteroids on Earth-crossing orbits.
Okay, thank you. And so good afternoon, everyone. So I will be talking about tidal disruptions, and I noticed that Eric already mentioned one of the key papers that I will be talking about. So this is work that I've been doing together with Kevin Walsh, so he should get not a little credit, but a lot of credit also. Mark was talking about this in the morning, and maybe some others have also been telling that we have an offset in the fireballs that we detect and the rate of fireballs and the predictions for impacts by small NEOs from asteroid survey data. And this has been shown both with this plot on the left-hand side by Alan Harris and Paul Chodes in 2021, and also earlier already, and also newer models by David Nesvorny show the same thing. So basically, the end result or outcome of these analyses is that we cannot find a match with the existing tools that we have and the existing approach that we have to population models without doing something. And if we, of interest, for instance, for Apophis, we know that these models, which are well in line in the Apophis size scale, predict that an object of Apophis size should impact roughly every 200,000 years. And when you scale that to sort of the encounter distance, these encounters of objects of this size should happen every 7,000 years. And yet we're here and have barely started surveying for NEOs, and immediately we find one of these objects. So there's clearly something that we're finding rare events almost immediately when we turn up our telescopes to the skies. So a key thing here to remember is that if you're trying to heal or solve a problem, then the first thing you have to admit is that you have a problem. And as a population modeler, I'm happy to admit that we have a problem here with the models. And now, if we look at the population models, then this model that I show here on the left-hand side, we wanted to focus on the left side of the plot, showing that asteroids tend to disrupt when they get close to the sun. But if you look at sort of further away from the sun, at higher perihelion distances, then you note that the observations actually don't fit with any of the models, also at higher perihelion distances. And if you plot this, do the same plot slightly differently, then you get this histogram that that I show here with the blue curve with error bars, showing basically that we have an excess of asteroid detections at two specific perihelion distances, one at 0.7 AU and the other around 1 AU. And of course, those coincide with the semi-major axis of Venus and Earth. What you see in the background is basically an ensemble of objects from tidal disruption simulations and what their perihelion distances are. And you see that there are these same peaks that if they get close to to Venus or Earth, then you tend to get more tidal disruptions. And this is not a fit in any way, this is just overlaying the two different distributions. And just to guide your eyes, I just point out that Apophis is roughly there, so it could have had an encounter with Venus, which would have destroyed it, maybe could destroy it or something. It could be caused by or produced by a tidal disruption event. I will show a few more slides of the same thing. This is just to note that the tidal disruptions of NEOs have been suggested already for decades, so this is nothing new. The only problem that we've had so far is that we haven't actually had any evidence that they would actually affect the population at large. We have them for individual case or seen these sort of shape similarities between simulations and radar observations. And we've also, there has been work to understand how tidal disruptions could produce binaries and to figure out if they could produce asteroid families, and basically saying that neither of these seem to happen in too great numbers. At least this has been the opinion for some time, but we'll see going forward how that evolves. So if we look more carefully at those sort of the excess that we see of objects that get close to the Earth and could produce the excess in the orbital element space, then if you look here in this quartet of plots, I show Venus encounters on the left and Earth encounters on the right, and then eccentricity on the top row and inclination distribution on the lower level. And again, there's no fits in here. It's just showing sort of overlapping two different histograms and showing that they basically agree. The orbital elements, both in Q or in Q, E, and I, basically overlap with tidal disruptions. So, and again, Apophis, if you plug it in there with its orbital elements, then it sort of lies nicely in, or overlays exactly on top of the peak. There we go. So now if we want to fix the population models, then the only thing that we can do in the models that I've been involved in developing over the years is that we actually, what we're fitting is basically just parameters describing the size distributions. And what we actually, if we want to change something, then we need to change the orbit distributions that we put in. So we just add in more source regions, which in practice means more orbit distributions, steady state orbit distributions corresponding to those sources. And we did sort of produce some sort of ad hoc orbit distributions of different ages for tidal disruption events at the Earth and Venus, and redid the fits and got this outcome. So now we have in the background with gray, we have the original perihelion distribution in perihelion distance, and this on the y-axis is the difference between the observed and predicted number of NEO detections here. So now if you do quickly in your head the statistics, then this actually aligns. I mean, there is some scatter, but it's perfectly fine given the statistics. So it seems that the tidal disruptions could explain what we're seeing, this excess, and I realize that this is just one of the explanations that could be happening. But the one thing that actually supports this is that when we also then look at the size distributions, then it turns out that we are actually having a peak and these all curves are just the same as I showed previously, but just for different sizes. And now we get a bigger offset when we go to smaller objects, which would make sense. You disrupt a large object and you produce more fragments. And this is exactly what we again see. And Apophis, if you plug it in there, then it happens to lie exactly on the highest peak in what we model. I should remind you that this is, I don't really even myself trust that this is a real thing. It's more a coincidence, but it's an interesting coincidence, if nothing else. So there has been also other, we're not the only ones who have done this since this initial discovery. David Nesvorny did a model soon after us and found that he also sees an excess of asteroids or near-Earth asteroids exactly on the kinds of orbits where we should see tidal disruption fragments. So on the left you see the orbit distribution of something that his model cannot explain. So that's the probably or could be tidal disruption events or the fragments from tidal disruption events. And I'll just leave up the conclusions, and I think what I should highlight here is that the tidal disruptions may solve the discrepancy between the impact predictions based on one side small NEOs and on the other side on the observed rates of impacts by small meter scale objects. But there are, of course, other kinds of data from the meteor and meteoroid community. There has been 2 papers talking about this, and they basically got a bit not really conclusions in agreement with each other, but I think what they both concluded on was that there's not enough data yet to sort of take or make a final conclusion. So we're still investigating this issue, and that's the end. Thanks.
We have time for one quick question, if anybody would like to step up. Okay, in that case, Okay, thank you very much. And let's move to our next speaker. So do we have Sophie Diem? Okay, excellent. So she will be telling us about a near-Earth object model calibrated to Earth impactors.
Hello, everyone. Thank you very much. I'm very happy to be here. This is my first Planetary Defence conference, and I just want to take a second to say that this has been a very welcoming and nice community to come and chat to, so I hope that you enjoy my talk. First of all, going to continue talking about the near-Earth object models that we have working on top of the work that Mikhail was just introducing there. So just to give a bit of background and how we have near-Earth objects in the first place. So the nominal idea is that we have asteroids on main belt orbits, and these are very stable, and eventually, and over time, they are brought onto Earth-crossing orbits. Some of the main drivers for these are mean motion resonances with Jupiter, secular resonances with Saturn, having asteroid families in the inner part of the main asteroid belt, and also Jupiter family comets as well can make their way to near-Earth space. But looking a little bit closer at the main asteroid belt, we know that it is not the same everywhere. There is a bit of a compositional gradient to make it very simple. We have some more dark asteroids near the outer belt or some more lighter asteroids in the inner belt. So in our near-Earth object models, we're really figuring out what parts of the main asteroid belt are we sampling when we are looking at the near-Earth object population. So Mikhail's model in 2018, which you've probably seen that mentioned through quite a few talks so far in this conference, figured out sort of the ratios of different source regions that contribute to the near-Earth object population. So on the graph on the left-hand side, the x-axis is size, and so here are a couple of the inner belt sources, just to group them all together, some asteroid families, mean motion resonances, and a secular resonance. And they've also figured out the contribution of some of the outer belt sources. And altogether, bringing it together, we can see that we have a good idea of, for some of these large asteroids, the fractional contribution of each of these main belt regions that we're sampling. But what if we wanted to look at the smaller sizes? What if we wanted to extend these models down? Well, why we would be interested in doing that is that meteorite droppers can extend down to about 10 centimeters in size, and we have civilian hazards, which are the main focus of this conference, that can extend down to roughly maybe 10 meters in size or so. And how do we make these models? So the kilometer-sized asteroids, these models are calibrated using telescopically observed asteroids, but even through the many more surveys we have, we're pushing the boundary of how small we can look, but there is a limit at the moment. Now, in the sort of 10 meter to 1 meter size, we have satellite and infrasound data, so we can see these objects when they impact the Earth. However, this happens fairly infrequently, so we don't have quite enough data in this middle range to really constrain sort of what's going on. And then as we go to smaller sizes, we can look at meteors and fireballs and bolides through cameras, so through just visible light. And so what my PhD research and this talk focuses on is what is happening at these small sizes and how can we use this information to constrain what's happening in the middle sizes. So how do we do this? I'm part of the Desert Fireball Network, and this is what our cameras look like. You can see a solar panel, and you can see a large metallic tripod, and on top of that tripod is a box that contains a Nikon camera. And these are where our telescopes are located around the world in the Global Fireball Observatory. And these are our observations. So the images are taken with fisheye lenses, and so what you can see here is a nice bright fireball across the sky. And this is a long exposure image with, and the gaps you're seeing in the fireball are an encoded timing sequence that help us with our triangulation. And so if you're interested in more fireball science, I hope you can check out Thomas Stevenson's poster looking more at the airburst hazards. And if you're interested in more Australian science, I hope you can check out Ed Cruzen's poster on the Southern Hemisphere research. But what these observations can give us is they can give us orbits of all of the objects we see impacting the Earth. Here you're seeing a time lapse of these blue dots, where they are in space before they impact the Earth, and the Earth is on that third blue line out from the sun. And so we are able to take all of our observations and get orbits in a similar way that you guys can take telescopic observations and also get orbits. Some of our constraints is that we can only get Earth-crossing orbits, and we also intrinsically measure mass and not size. So we've got a bit of constraint on mass, but then we don't understand the diameters of what we're working with. And so what my model used as data was more than 1,200 orbits of objects that were greater than 10 grams in size. We were accounting for the Earth impact probability and also the brightnesses, as in it's easier to see a brighter thing than a fainter thing. And what I have here is two plots showing the orbital element's semi-major axis eccentricity, or versus inclination. And we're showing that we have a lot of data that is along the line of perihelion equals 1 AU, because that is where the Earth orbits. And we also have data, but we have data that extends beyond that. And the weighting of our data accounts for the fact that higher inclination orbits or orbits further out are less likely to be impacting the Earth. And so we've taken this sort of de-biased data set, and we're comparing it to these escape regions, source region, orbital distributions that are created from the simulation. So we're using the ones that are from the NEO-mod models from David Biasvorny's work. And so we took the simulated distributions of the orbital elements of NEOs from 12 escape regions. And what we're doing is we're comparing that with our data. Now, because we're looking at smaller objects, we are taking into account some physical processes, so low perihelion disruptions that is taken into account for bigger objects, but we're wanting to see could that be needed to be included for the smaller object model, and we also are taking into account collisions as well. And so what we're showing here is sort of the difference in the orbital element distribution of NEOs that have and have not undergone collisions during their evolution. So this is the distribution coming from like the new 6 resonance. And what I want to point out to you in the bottom right-hand plot, there's more of a gap in the top left corner. And so that's showing that there are less low semi-major high inclination orbits. There are less evolved orbits when you have collisions that are depleting your population. And so taking these distributions from all these different sources, we fitted a model to the 6 most significant sources that could explain the data set, 25 parameter model solved with multi-nest, and this is the plot of the posterior marginal distributions. And just one thing I want to point out is that we have a lot of degeneracy, unfortunately, at the larger sizes of our model, and that's because we don't have as much data with the bigger objects because they impact less frequently. And this has some implication as to how we want to interpret the data. Interpret the model results, sorry. And so looking back at Mikhail's model, if we extrapolate down, these are sort of the results that we're seeing. The first thing to point out is that we can see the inner belt dominance continues down to the smaller sizes. And we had a better fit for source region, which simulates a whole bunch of inner belt weak resonances as opposed to the Hungaria family. But that's a difference in methods, perhaps. We saw the best fit collisional lifetimes to be 3 million years for our larger sizes, and a transition that was preferred as the best fit model down to 1 million years for the smaller sizes. We saw this transition at about 7 centimeters or 0.6 kgs. We won't read too much into the specific value, but as a population as a whole, this is the best fit because we will be sampling objects of many different compositions and types. And this is as expected from collisional models, which is unsurprising because collisional models are well constrained to laboratory experiments that happen on rocks about the same size as what we're modeling. So everything is looking good so far. Unfortunately, we do have some quite large error bars at our larger sizes. So hopefully over time, we can continue this work, including more data, including data from different sources and different fireball networks. But this really goes to show the strength of what we can contribute with our fireball networks. So just to summarize, so we debiased some fireballs from the Global Fireball Observatory. We confirmed that inner belt dominance should extend across the decameter, 10-meter near-Earth objects. We have observed the collisional lifetime transition from 3 million years down to 1 million years as the objects get smaller and smaller. And this can create a sampleable output, which a lot of people in the audience have already been using, Mikhail Gramberg's model, and so hopefully this is another tool for our community to use. And what's just showing here on the right-hand side, which is flicking through, is sort of a heat distribution of if you were to sample the model. And so I will finish with that. Thank you very much.
Really nice, Sophie. So you can probably submit some questions online chat, and perhaps authors can respond to this during maybe tomorrow or during the course of this conference. And we have the last talk for today by Peter Janiskens, and this is a review on instrumentally recorded meteor falls as geological hand specimens of asteroid families.
Nice to be back in Africa. And in this talk, I want to convince you, for all the non-astronomers in the audience, that studying meteorite falls and studying these small asteroids seen coming in are great ways to contribute to planetary defense, especially because Africa was already hit twice. I mean, one impact in Sudan in 2008, and there was one impact in Botswana, 2018. So this is actually about the meteorite, the observed trajectories, like Sophie was describing, the observed trajectories that were recovered, for which somebody found a meteorite. And if you have that meteorite in hand, then suddenly you have a whole bunch of extra information. These projects are great for collaborations. We're already doing that. Bring scientists involved, bring the governments involved to help find the meteorites. But this also provides specific data that we can use. And what has come out of all this is this sort of geologic map of the asteroid belt. We are working to identify which of all these asteroid families have what type of meteorite associated with them. And this is on the right-hand side, you see the asteroid colors, basically a representation of the spectra of asteroids. On the left-hand side, you see the families that we have identified so far. And you see there's still a lot of questions, so we need a lot more data. Now, if you look at the distribution of the fragments, what's plotted on the horizontal axis is semi-major axis, but basically orbital period. So you go from just outside of Mars orbit to halfway Jupiter's orbit, further out into the solar system. That means that it takes longer for you to go around the sun. And so what you're looking at there is orbital period. And vertical is plotted the inclination, so it's how steep the asteroid orbit sits to the ecliptic plane. And you can see these empty areas there, these lines, those are the resonances that Sophie mentioned. Now what happens is, you have a collision somewhere in the asteroid belt. Each piece now, each small fragment, starts seeing the sun at noon. It spins a little bit, and then it radiates the heat at the hottest time of the day, say 3 o'clock. So that means you're going to be pushed that way. Or if you spin the other way, you're going to radiate your energy there, and so you're going to be pushed that way. That means that you're going to increase or decrease the orbital period. And you can see that in the picture, because all these asteroid families are sort of spread out in inclination. They cover a range of orbital periods. Let's see how this works. So far we've had a couple of cases where the asteroid was seen coming in, which gives you really good orbit. In the case of TC3, back in the day, the predictions were a kilometer off from where the meteorites fell on the ground. It turned out that the gravity field of the Earth was not well enough described. So after that was fixed, the precision improved a lot, and the last two impacts in France, Normandy, and in Germany allowed direct comparison of the observations that Sophie was describing and the asteroid observations. And it turned out there was still a discrepancy of a few tens of meters. And both parties were adamant that, no, this is what we're finding. Turned out that astronomical observatories were not reporting the altitude of the observatory in the same coordinate system. So the Minor Planet Center had to update all that data. So I think a lot of these small impacts have really been good test cases, exercises. A lot of that has now gone fairly smooth. exactly with the last one, 2024, wire4. So in the future, I think these cases are really good to somehow involve the disaster response effort, because when these events happen, there's a lot of attention for these cases locally. So most of the information we get is not from these asteroids we've seen coming in, but from regular fireball observations like this. And this is the number of orbits now for which we have meteorites and all the groups in the world that are participating to it. So we have 75. That means that as of today, we have 28 H-chondrites, 20 L-chondrites, and 6 L-chondrites, and 5 LLL, which are also L-chondrites, basically. So I'll concentrate on those 3 types here. Now, as soon as you have a meteorite in hand, then you can measure the cosmic ray exposure age. You can determine how long this rock was in space, because the moment a collision happens, or a breakup happens, it gets smaller than 2 meters. The rock gets radiated by cosmic rays. Cosmic rays penetrate about 1 meter into the rock. So once your rock is smaller than 2 meters, then you start building up these really weird elements. So oxygen atoms, for example, turn into beryllium, and 10 beryllium, and you can measure the concentration of that. And if you do that, then you can tell you how long that rock was in space. And on the asteroid side, we can use this Yarkovsky effect, what I just described. If you spin one way or spin the other way, how fast you change your orbit is a function of size. The bigger ones are really hard to move, the small ones are easy. You can use this to get the ages of families. Okay, this diagram shows now the same major axis, orbital period on the bottom, and inclination on the side, on one end. And on the other side, you see the cosmic ray exposure age, so how long the rock was exposed. These are the HEDs. These are meteorites we know come from Vesta, or the Vesta family. That's that big green blob that you saw. That's very unique in asteroid belt. And sure enough, we see that we have 5 HEDs so far, including the one from Botswana, and a recent fall here in South Africa, in Queba. All those cases line up very nicely in inclination with the inclination of the HEDs. We think, by the way, that they're not from the family, because those are all very small. We think that they're coming from Vesta itself in this case. So this works. The LLLs seem to come from the inner side of the asteroid belt. There's a big family called Flora, has LL-type spectra, and sure enough, inclinations sort of line up. You can see there's a bunch of them that are quite different, and that is because once you have your collision, then you have your Yarkovsky that brings you to the resonance. At that point, the orbit very quickly changes. The aphelion goes out, perihelion comes in, and then you can start having collisions with the Earth and with Venus. And Earth and Venus close encounters can really change your inclination. And so you get sort of a dispersion of inclination. The symmetry goes down and the inclination goes up. So all of that works. It also works for the really big things. Flora, 1 kilometer size LL asteroids are also coming from the inner side of the asteroid belt, a new 6 residents. So Flora looks to be the source of those. Now with H-chondrites, there's something else going on. The H-chondrite-like S-class families seem to come from high in the asteroid belt and out of the 3-to-1 resonance. And that's not the case with the meteorites we see here on Earth, the small ones. All these blue ones come from beyond the 3-to-1 resonance. And it's really stunning. You don't see that with any other meteorite type. And you can also see that the dispersion in the perihelion distance, for example, increases the further you go away from the 5-to-2 resonance. So this source sits just outside of the 5-to-2 resonance. And there is a family there called Coronis that has H-like spectra, people claim, and that perfectly fits the inclination distribution. And so it turns out that from those blue points, we do not have just one cosmic ray exposure age. So there was not one collisions. There were at least 3 different ones. And it turns out there are actually 3 different collisions, like clusters in the Corona family. And those 3 clusters, I think we all 3 see. So we see in our meteorites, 10 centimeter to meter size objects, we see the debris from the same collisions as what gives some of our near asteroids. And we can identify which one is which. Not all H-chondrites come from there. There's also a group that sits high in central main belt, the source. 4 of those have a 6 million year cosmic ray exposure age, 2 18 million years. I think I've identified a 6 million year one because it looks like that's Nele, the Nele asteroid family. The 18 million year one I'm not sure about. So if anybody knows an 18 million year debris field high in the asteroid belt, let me know. And then there is this inner asteroid, this inner source of H-chondrites, which have a cosmic ray exposure age of 35 million years. And that's a really interesting puzzle because I think I don't see a 35 million year debris field in Coronis. I think I need one in the inner asteroid belt. And that basically means to basically explain these, including Narashino in Japan. And I think that these are coming from Massalia. It's been claimed that Massalia is L-type and not H, but that's a matter of interpretation, I think. Because this is some of the data from the Massadadol paper last year in Nature. You can see that they measured the olefin and pyroxene ratios. And this is how they interpret it. So Massalia is L. But I think the way it needs to be interpreted is this. There's a sort of a gap between the L's and the H's. And that's what you see in the asteroid family. So I think Massalia is H. And that means that I'm left with Herta as the source for the L's. Herta is a good candidate for the fact that the L's 468 million years ago were just a massive amount of meteorites on Earth. And I think that Herta is where that source was. So that leaves us sort of at this purple regime there. EOS family, fascinating different spectral type between all these S's, which are the orange ones, and the carbonaceous chondrites ones, the C's. EOS sort of sits in between. And they've been set to produce CO, CV, and CKs. So in April last year, there was a meteorite fall in Arizona, and a guy claimed that they had found meteorites from Mars in our strewn field. But I'm looking at the orbit, and the orbit is coming 15 degrees inclined out of the outer asteroid belt. So I wrote to these meteorite hunters. I said, no, I don't think that can be the truth, because I would expect to find a CV, CO, CK. And sure enough, with excitement about Martian meteorites, people went back into the field, found a meteorite, and it turned out to be a CK. So this is the first time that a meteorite orbit was informative about what meteorite you find on the ground. And I can do the same thing with 2024 YR4. I think it's an H chondrite, but there's a small chance too that it's an L chondrite. So this sort of information needs to be, quantified. But I think if Andy's observations are consistent with an H chondrite, then I'd be very happy. Thank you.
Okay, well, we can thank the speakers one more time, and I think that Max and I bid you farewell for this session.
Yes, thank you again for an insightful session. Just some quick notes. Before we go downstairs for the group picture, I have a few winners to announce. First of all, we had a virtual challenge, the Streaming in Style, where we asked people watching from online to submit their workstations, how they're watching, how they're interacting. And we have a winner here, and that's Tobekile Ngwane, who we heard earlier in the session. She won a $20 gift voucher. Congratulations. And for our in-person participants, we had the Eyes on the Ground photo contest, and we had a tie there. So we have two winners. That's Marta Ceccheroni for her Planetary Defense cherries, and John Fairlamb for the safari at Protea Hotel. So please come forward, pick up your gift bags, and then we will all go downstairs. So we will once we come downstairs, we keep going straight. We exit the building. We aim for the restaurant downstairs, but we keep left. And there's a photographer already standing. She will put us into place. Please take all your belongings, because from there we will move to the front of the hotel where we'll board the buses. As long as you registered for that, and you will tick off the bus, and that's all I have. So see you downstairs. Buses leave at 4:30, and we take the picture first. Thank you.